The largest object humanity has ever discovered spans 10 billion light-years. That measurement is not a theoretical estimate or a projection based on incomplete data. It is the observed extent of a structure so enormous that light leaving one end when the universe was young would still not have reached the other side today. This structure is called the Hercules Corona Borealis Great Wall, and its existence challenges some of the most fundamental assumptions we hold about how the cosmos is organized. When we look at the night sky, we see individual stars. With a telescope, we can resolve those stars into galaxies, each containing hundreds of billions of their own suns. With better instruments, we observe that galaxies themselves cluster together, bound by gravity into groups and clusters containing thousands of members. And with the most advanced surveys ever conducted, we have now discovered that even those clusters are not the final level of organization. They connect into filaments, sheets and walls that stretch across distances so vast that our traditional sense of scale simply fails. The Hercules Corona Borealis Great Wall is currently the largest known structure in the observable universe. It was not found by looking at visible light or by counting galaxies one by one. It was detected through gamma-ray bursts, the most energetic explosions in the universe, occurring in a pattern that revealed an underlying concentration of matter spanning a significant fraction of the observable cosmos. The structure's existence was confirmed in 2013, and since then, astronomers have struggled to explain how something so large could form in a universe only 13.8 billion years old. This is not a question of curiosity alone. The discovery of structures at this scale forces a confrontation with the limits of current cosmological models. According to the standard framework, the universe at its larger scales should appear smooth and uniform. Matter should be evenly distributed when viewed from far enough away. But the Hercules Corona Borealis Great Wall, along with other recently discovered giant structures, suggests that this assumption may be incomplete. Something in our understanding of cosmic evolution is missing, and finding it may require revising principles that have guided astronomy for decades. To understand what it means to discover the largest object in the universe, we must first establish how astronomers measure and categorize structures at cosmic scales. This is not a simple task. The methods used to determine the size of a mountain or even a planet do not apply when dealing with collections of galaxies spread across billions of light years. At these distances, measurement itself becomes an exercise in indirect inference, requiring tools and techniques that have taken centuries to develop. The fundamental unit of cosmic distance is the light year, the distance that light travels in 1 year, moving at approximately 300,000 kilometers per second. In 1 year, light covers roughly 9.5 trillion kilometers. This number is already difficult to grasp, but it serves only as a starting point. The nearest star system to our Sun, Alpha Centauri, lies about 4 light-years away. The Milky Way galaxy spans roughly 100,000 light-years from edge to edge. The nearest large galaxy, Andromeda, is approximately 2.5 million light-years distant. These measurements, while enormous by human standards, represent only the immediate neighbourhood of our cosmic address. Beyond individual galaxies, astronomers must contend with structures that contain thousands or even millions of galaxies. Measuring their extent requires identifying which galaxies belong to a given structure and which are merely along the same line of sight by coincidence. This is accomplished through redshift surveys, which exploit a phenomenon fundamental to modern cosmology. As the universe expands, light travelling through space is stretched, shifting its wavelength toward the red end of the spectrum. The greater the distance an object lies from us, the more its light has been stretched during its journey, and the higher its redshift value. By measuring the redshift of individual galaxies, astronomers can determine not only their distance, but also their three-dimensional position in space. The first major redshift surveys began in the 1970s and 80s, mapping thousands of galaxies and revealing for the first time that their distribution was far from random. Galaxies were not scattered evenly through space like dust particles suspended in air. Instead, they congregated along filaments and walls, surrounding vast empty regions called voids. The pattern resembled a sponge or a network of soap bubbles, with matter concentrated on the surfaces and emptiness filling the interiors. This discovery fundamentally changed our understanding of cosmic structure, revealing an architecture that had been invisible to all previous generations of astronomers. As surveys grew more sophisticated, the structures they revealed grew larger. The CFA Redshift Survey, completed in the late 1980s, mapped over 18,000 galaxies and discovered the Great Wall, a sheet of galaxies approximately 500 million light-years long. At the time, it was the largest known structure in the universe, but the Great Wall was only the beginning. Subsequent surveys mapped hundreds of thousands, then millions of galaxies, each new dataset revealing structures that dwarfed their predecessors. The Sloan Digital Sky Survey, which began observations in 2000, represented a quantum leap in cosmic cartography. Using a dedicated telescope in New Mexico equipped with advanced digital imaging technology, the survey mapped over 1 million galaxies in its first phase alone. The resulting three-dimensional map revealed structures of staggering extent, including the Sloan Great Wall, discovered in 2003. This structure measured approximately 1.4 billion light-years in length, nearly 3 times the size of the original Great Wall. For several years, it held the record as the largest known structure in the universe. But how do astronomers determine where one structure ends and another begins? This question is more complex than it might appear. Unlike a planet or a star, a galaxy wall or filament has no sharp boundary. It is a region of enhanced density, a concentration of matter that gradually fades into the lower density regions surrounding it. Defining its edges requires establishing statistical criteria, determining at what point the density of galaxies drops below a threshold that separates the structure from its environment. Different researchers may use different thresholds, leading to varying estimates of a structure's size. Furthermore, the structures themselves are not static. The universe is expanding, carrying galaxies apart from one another at rates that increase with distance. When astronomers measure a structure spanning 1 billion light-years, they must specify whether they mean the distance as it existed when the light we observe was emitted, the distance as it exists today after billions of years of expansion, or some other metric entirely. These distinctions matter enormously at cosmic scales, where expansion can cause the current distance between two objects to differ significantly from the distance their light has actually travelled. The tools used to detect and measure these structures have evolved dramatically over time. Early surveys relied on photographic plates and manual analysis, limiting the number of galaxies that could be catalogued. Modern surveys use charge-coupled devices capable of capturing millions of pixels simultaneously, combined with automated software that can identify and measure galaxies without human intervention. Spectroscopic instruments, which spread light into its component wavelengths to measure redshift, have been multiplied through fibre optic technology that allows hundreds or even thousands of spectra to be captured at once. Despite these advances, measuring the largest structures remains challenging. The Hercules Corona Borealis Great Wall was not discovered through a traditional redshift survey of galaxies. Instead, it was detected through the distribution of gamma-ray bursts, the brief but incredibly energetic flashes of radiation produced when massive stars collapse or when neutron stars merge. Gamma-ray bursts occur in galaxies, and their distribution across the sky should reflect the distribution of matter in the universe. When astronomers analysed data from gamma-ray observatories, they found an unexpected concentration of bursts in a region spanning the constellations Hercules and Corona Borealis, suggesting an enormous underlying structure. This method of detection introduces its own uncertainties. Gamma-ray bursts are rare events, and the sample size is limited. The statistical significance of the observed concentration has been debated, with some researchers questioning whether the structure is real or an artifact of incomplete data. Subsequent analyses have supported its existence, but the Hercules Corona Borealis Great Wall remains less well characterized than structures discovered through direct galaxy surveys. Its estimated size of 10 billion light-years is based on the angular extent of the gamma-ray burst concentration combined with redshift measurements that place it at a distance corresponding to a time when the universe was roughly 4 billion years old. The challenge of measuring cosmic structures extends beyond technical limitations. At the largest scales, we confront a fundamental boundary. The observable universe has a finite size, determined by the age of the cosmos and the speed of light. Light from regions beyond approximately 46 billion light-years away has not had time to reach us since the Big Bang, no matter how far it has travelled. This means that any structure approaching this scale becomes impossible to fully map, as portions of it may lie beyond our cosmic horizon. The Hercules Corona Borealis Great Wall, at 10 billion light-years, occupies roughly 1/9 of the observable universe's diameter, raising questions about whether even larger structures might exist beyond our view. A single galaxy is an island of stars, gas and dust bound together by gravity. Our own Milky Way contains somewhere between 200 billion and 400 billion stars, along with vast clouds of molecular hydrogen where new stars continue to form. It spans 100,000 light-years and has a mass equivalent to roughly 1.5 trillion suns when dark matter is included. By any human measure, a galaxy is enormous beyond comprehension. Yet in the hierarchy of cosmic structure, a galaxy is merely a building block, a single brick in a wall that stretches across the observable universe. The recognition that galaxies exist as distinct entities outside our own is surprisingly recent. Until the 1920s, astronomers debated whether the faint spiral nebulae visible through telescopes were clouds of gas within the Milky Way or separate stellar systems at vast distances. The question was settled in 1924 when Edwin Hubble measured the distance to the Andromeda Nebula using Cepheid variable stars, a class of pulsating stars whose intrinsic brightness can be determined from their period of variation. Hubble's measurement placed Andromeda far beyond the boundaries of our galaxy, establishing that the universe contained countless other galaxies comparable to our own. This discovery expanded the known universe by orders of magnitude almost overnight. Suddenly, the Milky Way was not the entirety of creation, but merely one galaxy among billions. Subsequent observations revealed that galaxies come in a variety of forms. Spiral galaxies like our own feature rotating disks of stars and gas with prominent spiral arms. Elliptical galaxies are more spherical or elongated, containing older stellar populations and relatively little gas for new star formation. Irregular galaxies lack the symmetry of either type, often showing signs of gravitational disruption from encounters with neighbouring systems. Each type represents a different evolutionary pathway, shaped by initial conditions and subsequent interactions. The distances between galaxies vary enormously. The Milky Way and Andromeda are separated by approximately 2.5 million light-years, but both belong to a small collection of galaxies known as the Local Group. This gravitationally bound system contains more than 80 known members, most of them dwarf galaxies far smaller than the two dominant spirals. The Local Group spans roughly 10 million light-years, a volume of space that might seem vast but represents only the immediate vicinity in cosmic terms. Beyond the Local Group, other galaxy groups and clusters extend in every direction, each containing its own collection of gravitationally associated members. Galaxy groups typically contain a few dozen members, while galaxy clusters can contain hundreds or even thousands of galaxies. The nearest large cluster to our own Local Group is the Virgo cluster, located approximately 54 million light-years away. The Virgo cluster contains over 1,000 confirmed galaxies, dominated by the giant elliptical galaxy Messier 87 at its centre. The cluster spans roughly 15 million light-years and has a total mass equivalent to over 1 quadrillion suns. Its gravitational influence extends far beyond its visible boundaries, affecting the motions of galaxies throughout the local volume of space. The Virgo cluster is itself part of a larger structure known as the Virgo supercluster, which includes the Local Group and dozens of other galaxy groups and clusters spread across 110 million light-years. For decades, astronomers considered the Virgo supercluster to be our cosmic home, the largest structure to which our galaxy belonged. But in 2014, a team of researchers led by Brent Tully published a study that redefined our understanding of large-scale structure. Using precise measurements of galaxy motions, they mapped the gravitational basin within which galaxies flow toward common attractors. The result was the identification of a much larger structure called Laniakea, a Hawaiian word meaning immense heaven. Laniakea contains approximately 100,000 galaxies spread across 520 million light-years. It includes not only the Virgo supercluster, but also the Hydra Centaurus supercluster, the Pavo Indus supercluster, and several other major concentrations of galaxies. All of these systems are moving toward a gravitational focal point known as the Great Attractor, a region of enhanced mass located approximately 250 million light-years away in the direction of the constellation Centaurus. The Great Attractor itself is not a single object, but a concentration of galaxy clusters whose combined gravity pulls surrounding matter toward it at velocities of several hundred kilometers per second. Yet even Laniakea is not the largest structure in the universe. It is merely the supercluster to which we belong, one of millions of superclusters distributed throughout the observable cosmos. The arrangement of these superclusters reveals the true architecture of the universe at its grandest scales. They are not scattered randomly through space, but are organized into an intricate network of filaments, walls, and voids known as the cosmic web. This structure is the largest pattern of organization in existence, the framework upon which everything else is built. The cosmic web emerges from the distribution of matter in the early universe. Shortly after the Big Bang, matter was distributed almost uniformly through space, but not perfectly so. Tiny fluctuations in density, originating from quantum processes during the first moments of cosmic expansion, provided the seeds for all future structure. Regions with slightly higher density exerted slightly stronger gravitational attraction, drawing in surrounding matter and becoming denser still. Over billions of years, this process amplified the initial fluctuations into the structures we observe today. Computer simulations of cosmic evolution reproduce the cosmic web with remarkable fidelity. Beginning with initial conditions derived from observations of the cosmic microwave background, these simulations track the gravitational interaction of billions of particles representing dark matter and ordinary matter. As simulated time progresses, matter collapses into halos, which merge to form larger halos, which eventually host galaxies and galaxy clusters. The distribution of these simulated structures matches the observed universe with striking accuracy, forming the same pattern of filaments, walls, and voids seen in large-scale galaxy surveys. The filaments of the cosmic web are the highways along which matter flows. They connect galaxy clusters like threads connecting beads on a necklace, channeling gas and dark matter from low-density regions toward the massive concentrations at their nodes. Individual filaments can extend for hundreds of millions of light-years, containing countless galaxies strung along their length. Where multiple filaments intersect, the densest concentrations of matter accumulate, forming the massive galaxy clusters that anchor the cosmic web. Walls are sheet-like structures that form where filaments connect across broader regions. The original Great Wall discovered in the 1980s is an example of such a structure, a flattened concentration of galaxies extending across hundreds of millions of light-years. Walls are less dense than filaments, but contain more galaxies simply because they occupy larger volumes. They represent another level of organization in the cosmic hierarchy, intermediate between individual clusters and the largest structures yet discovered. Surrounding the filaments and walls are voids, vast regions of space containing very few galaxies. Voids are not completely empty, but are significantly underdense compared to the cosmic average. They typically span 100 to 300 million light-years and occupy the majority of the universe's volume. The matter that once filled these regions has been gravitationally evacuated over cosmic time, flowing along filaments toward the denser concentrations that define the web's structure. Voids continue to grow as the universe ages, becoming emptier while the filaments and walls become more pronounced. The recognition that galaxies are organized into this hierarchical structure has profound implications for cosmology. It means that the universe is not simply a collection of randomly distributed objects, but a system with architecture, a pattern that reflects the physical processes governing its evolution. Understanding this pattern requires understanding the nature of gravity, the properties of dark matter, the expansion history of the cosmos, and the initial conditions established during the Big Bang. Each level of structure, from individual galaxies to superclusters to the cosmic web itself, provides evidence about these fundamental aspects of our universe. And at the apex of this hierarchy, structures like the Hercules Corona Borealis Great Wall pose questions that current theories struggle to answer. Galaxy clusters represent concentrations of matter that dwarf anything within our immediate cosmic neighborhood. While the local group contains approximately 80 galaxies spread across 10 million light-years, a typical galaxy cluster packs hundreds or thousands of galaxies into a similar volume. The largest clusters contain several thousand member galaxies, bound together by gravity so powerful that even light itself struggles to escape from the deepest regions near their centers. These clusters are the most massive gravitationally bound objects in the universe, and understanding their properties is essential to comprehending the structures that lie beyond them. The mass of a galaxy cluster extends far beyond its visible galaxies. When astronomers first attempted to measure cluster masses in the 1930s, Swiss astronomer Fritz Zwicky encountered a puzzle that would take decades to resolve. By observing the velocities of galaxies within the Coma cluster, Zwicky calculated how much mass would be required to keep them gravitationally bound. The answer was startling. The cluster appeared to contain far more mass than could be accounted for by its visible galaxies. Zwicky proposed that some form of unseen matter, which he called dark matter, must provide the additional gravitational pull. This hypothesis was controversial at the time, but subsequent observations have confirmed that dark matter dominates the mass of galaxy clusters by a factor of roughly 5 to 1. The visible components of a galaxy cluster include not only galaxies but also a diffuse medium of hot gas that pervades the space between them. This intracluster medium consists primarily of hydrogen and helium, heated to temperatures exceeding 10 million degrees. At such extreme temperatures, the gas emits X-rays that can be detected by space-based observatories. X-ray observations have revealed that the intracluster medium contains more mass than all the cluster's galaxies combined, though both are dwarfed by the invisible dark matter halo that envelops the entire system. The Virgo cluster provides a relatively nearby example of cluster structure. Located 54 million light-years away, it is close enough for astronomers to study individual member galaxies in detail, while still representing a massive system in its own right. The cluster's central region is dominated by Messier 87, a giant elliptical galaxy containing several trillion stars. Messier 87 hosts a supermassive black hole with a mass equivalent to 6.5 billion suns, one of the most massive black holes ever measured. This black hole was the subject of the first direct image of an event horizon, captured by the Event Horizon Telescope collaboration in 2019. Moving outward from the Virgo cluster, we encounter progressively larger and more massive systems. The Coma cluster, located approximately 320 million light-years away, contains over 1,000 large galaxies and thousands of smaller dwarf galaxies. Its total mass exceeds 700 trillion solar masses, making it one of the most massive nearby clusters. The central region of the Coma cluster is dominated by two giant elliptical galaxies, NGC 4889 and NGC 4874, which are gradually merging as the cluster evolves. At greater distances, even more massive clusters have been identified. The El Gordo cluster, discovered in 2012 at a distance of approximately 7 billion light-years, is actually two clusters in the process of colliding. The combined system has a mass exceeding 2 quadrillion solar masses, making it the most massive known cluster at such great cosmic distances. The collision between its component clusters has heated the intracluster gas to extreme temperatures and separated dark matter from ordinary matter in ways that provide crucial evidence for dark matter's existence. Galaxy clusters do not exist in isolation. They are connected to one another by the filaments and walls of the cosmic web, and they often occur in groups called superclusters. The concept of a supercluster has evolved as observations have improved. Early definitions identified superclusters simply as concentrations of galaxy clusters, regions where clusters appeared more numerous than average. The Shapley supercluster, for example, contains approximately 30 galaxy clusters, concentrated in a region roughly 650 million light-years away. It is one of the most massive concentrations of matter in the nearby universe, and contributes significantly to the gravitational pull that affects our own local group. More recent approaches define superclusters based on gravitational dynamics, rather than simple clustering. The Laniakea supercluster, identified in 2014, was delineated by mapping the gravitational basins within which galaxies flow toward common attractors. This dynamical definition provides a more physically meaningful boundary than simple density enhancements, identifying regions that are gravitationally coherent even if their member galaxies span enormous volumes. The transition from clusters to superclusters marks an important threshold in cosmic structure. Galaxy clusters are gravitationally bound systems, meaning that their member galaxies will remain associated indefinitely, despite the expansion of the universe. The gravitational attraction within a cluster is strong enough to overcome cosmic expansion, keeping the system intact. Superclusters, however, are generally not gravitationally bound. The expansion of the universe is gradually pulling their component clusters apart, and over cosmic timescales, most superclusters will disperse rather than collapse into more concentrated structures. This distinction has profound implications for the formation and evolution of large-scale structure. Gravitationally bound systems can grow through mergers and accretion. drawing in surrounding matter and becoming more massive over time. Galaxy clusters have been growing in this way since the early universe, with smaller clusters merging to form larger ones and individual galaxies falling into existing clusters. But at the supercluster scale, cosmic expansion begins to dominate over gravitational attraction. Structures at this scale represent the approximate limit of gravitational organization in the universe, or so astronomers believed until the discovery of structures far larger than any supercluster. The Sloan Great Wall, identified in 23, was the first structure to clearly exceed the expected limits of gravitational organization. Spanning approximately 1.4 billion light-years, it contains multiple superclusters connected by dense filaments of galaxies. Its existence raised questions about how such an extended concentration of matter could form in a universe where expansion should prevent structures above a certain size from developing. The Sloan Great Wall was discovered through analysis of data from the Sloan Digital Sky Survey, which mapped the positions and distances of millions of galaxies in the northern sky. By constructing three-dimensional maps of galaxy distribution, researchers identified this enormous structure stretching across the survey volume. Its discovery demonstrated that the cosmic web contains features far larger than individual superclusters, concentrations of matter that span significant fractions of the observable universe. But the Sloan Great Wall was only the beginning. Subsequent discoveries revealed even larger structures, each one challenging assumptions about the limits of cosmic organization. The Huge Large Quasar Group, identified in 2013, spans approximately 4 billion light-years and contains 73 quasars arranged in an elongated concentration. Quasars are extremely luminous active galactic nuclei powered by supermassive black holes, and their distribution traces the underlying structure of matter in the distant universe. The existence of such a large coherent structure at such great distances suggested that enormous concentrations of matter existed even in the earlier universe. Then came the Hercules Corona Borealis Great Wall, detected through gamma-ray burst distributions and spanning an estimated 10 billion light-years. This structure exceeded all previous discoveries by a substantial margin, occupying roughly 1/9 of the observable universe's diameter. Its size was so extreme that many astronomers initially questioned whether it could be real, whether the observed concentration of gamma-ray bursts might be a statistical fluctuation rather than evidence of an underlying structure. But subsequent analyses have supported its existence, forcing cosmologists to confront a universe where structures of almost unimaginable scale appear to exist. The progression from galaxy clusters to superclusters to great walls represents a journey across orders of magnitude in scale. Each level reveals new properties and poses new questions, yet even the largest structures share common origins in the density fluctuations of the early universe, the tiny variations that gravity amplified over billions of years into the cosmic web we observe today. Understanding how this amplification produced structures spanning billions of light-years requires examining the web itself in greater detail. The cosmic web is not a metaphor. It is a physical structure, a network of matter that permeates the observable universe and organizes everything from individual galaxies to the largest concentrations of mass ever discovered. When astronomers map the positions of millions of galaxies in 3 dimensions, the pattern that emerges resembles nothing so much as a vast biological network, with dense nodes connected by elongated filaments and surrounded by empty voids. This architecture is the skeleton of the universe, the framework upon which all visible structure is built. The existence of the cosmic web was first glimpsed in the late 1970s and early 1980s, when redshift surveys began mapping galaxy distributions in 3 dimensions. Prior to these surveys, astronomers knew that galaxies were not uniformly distributed across the sky, but they lacked the distance information needed to determine whether apparent clustering reflected true physical associations or mere projection effects. Redshift measurements changed everything. By determining the distance to each galaxy through the stretching of its light, astronomers could construct genuine 3-dimensional maps of cosmic structure. The first results were surprising. Instead of finding galaxies scattered randomly through space with some moderate clustering, surveys revealed sharp concentrations and vast empty regions. The Botas void, discovered in 1981, was one of the first great voids identified, spanning approximately 330 million light-years with remarkably few galaxies within its volume. The original Great Wall, discovered in 1989, demonstrated that galaxies could concentrate into sheet-like structures extending hundreds of millions of light-years. These discoveries overturned the assumption that the universe would appear smooth and homogeneous when viewed at sufficiently large scales. The cosmic web consists of four primary components. Nodes are the densest regions, corresponding to galaxy clusters and superclusters where multiple filaments intersect. Filaments are elongated structures connecting nodes, containing galaxies strung along their length like beads on a string. Walls are sheet-like concentrations of galaxies that form where filaments connect across broader regions. And voids are the under-dense regions between these structures, containing far fewer galaxies than the cosmic average. The relative proportions of these components reveal the universe's large-scale organization. Voids occupy approximately 80% of the universe's volume, but contain only about 20% of its galaxies. Filaments and walls occupy the remaining 20% of volume, but contain roughly 80% of galaxies. This extreme concentration of matter into a relatively small fraction of space is a direct consequence of gravitational evolution, acting on the initial density fluctuations from the early universe. The filaments of the cosmic web are its most distinctive feature. They range in length from tens of millions to hundreds of millions of light-years, connecting galaxy clusters across vast distances. Individual filaments contain thousands of galaxies along with enormous quantities of gas that has never condensed into stars. This intergalactic gas, heated to millions of degrees by gravitational compression, represents a significant fraction of the ordinary matter in the universe. For decades, astronomers struggled to account for all the ordinary matter predicted by Big Bang nucleosynthesis, the so-called missing baryon problem. The discovery of hot gas within cosmic filaments has helped resolve this discrepancy, revealing that much of the universe's ordinary matter exists in a diffuse state between galaxies rather than within them. Mapping the cosmic web requires surveys of unprecedented scale and precision. The Sloan Digital Sky Survey, which operated from 2000 to 2014 in its original form and continues in subsequent phases, has mapped over 4 million galaxies and quasars across more than a third of the sky. The 2-degree field galaxy redshift survey mapped over 200,000 galaxies in the southern sky during the late 1990s and early 2000s. More recently, the Dark Energy Spectroscopic Instrument began operations in 2021 with the goal of mapping over 30 million galaxies and quasars, creating the most detailed three-dimensional map of the universe ever constructed. These surveys have revealed the cosmic web structure at progressively larger scales. At distances of a few 100 million light-years, the web appears intricate and detailed, with individual filaments and voids clearly resolved. At distances of several billion light-years, the pattern remains visible but becomes less distinct as individual features blur together. And at the larger scales, approaching the size of the observable universe itself, the question of whether the web continues or gives way to true homogeneity remains actively debated. The formation of the cosmic web is understood through a combination of theoretical models and computer simulations. The process begins with the density fluctuations imprinted during the inflationary epoch, the brief period of exponential expansion that occurred in the first fraction of a second after the Big Bang. These fluctuations, amplified by gravity over billions of years, produced the structures we observe today. The physics governing this evolution is well understood in principle, involving the gravitational interaction of dark matter, ordinary matter, and dark energy in an expanding universe. Computer simulations of cosmic structure formation have become increasingly sophisticated over the past 4 decades. The Millennium simulation, completed in 2005, tracked the evolution of 10 billion particles representing dark matter within a cubic volume 2 billion light-years on a side. The simulation successfully reproduced the cosmic web structure, including the distribution of galaxy clusters, the properties of filaments and voids, and the statistical patterns observed in real galaxy surveys. Subsequent simulations have incorporated additional physics, including the behavior of ordinary matter, the formation of galaxies within dark matter halos, and the effects of supermassive black holes on their surroundings. These simulations confirm that the cosmic web structure emerges naturally from gravitational evolution in an expanding universe dominated by dark matter and dark energy. Dark matter provides the gravitational scaffolding upon which the web is built. Because dark matter interacts only through gravity, it began collapsing into structures earlier than ordinary matter, which was initially coupled to radiation and prevented from collapsing. Once ordinary matter decoupled from radiation approximately 380,000 years after the Big Bang, it fell into the gravitational potential wells already established by dark matter, forming the galaxies and gas concentrations that trace the web's structure. The cosmic web continues to evolve today. Voids are expanding as matter flows out of them along filaments toward denser regions. Filaments are becoming more defined as galaxies stream along them toward cluster nodes, and clusters themselves are growing through mergers and accretion, becoming more massive as cosmic time progresses. However, this evolution is slowing. As dark energy increasingly dominates the universe's expansion, the growth of structure is being suppressed. Eventually, cosmic expansion will overcome gravitational attraction at all but the smallest scales, halting the evolution of the cosmic web and freezing its structure in place. Understanding the cosmic web structure is essential for interpreting the largest known objects in the universe. Great walls like the Hercules corona borealis structure are not independent entities floating in empty space. They are concentrations within the cosmic web, regions where filaments and walls converge to create extended overdensities spanning billions of light years. Their existence reflects the web's large-scale organization, the patterns imprinted by initial conditions and amplified by gravity over cosmic time. Yet the sheer size of structures like the Hercules corona borealis Great Wall poses challenges for current models. Simulations based on standard cosmological parameters produce cosmic webs with statistical properties matching observations at most scales. But they struggle to produce structures as large and coherent as the greatest observed walls, suggesting that either the observations are incomplete, the simulations are missing important physics, or our understanding of cosmic evolution requires revision. Resolving this tension requires better observations, more sophisticated simulations, and perhaps new theoretical frameworks that can accommodate structures of truly cosmic scale. The discovery of structures spanning billions of light years was not possible until technology advanced sufficiently to map the universe at such scales. For most of human history, the night sky appeared as a fixed dome of stars, unchanging and fundamentally unknowable. Even after the invention of the telescope in the early 17th century, progress in understanding cosmic distances came slowly. The tools required to detect and measure structures like the Hercules corona borealis Great Wall represent the culmination of centuries of incremental innovation, each breakthrough building upon those that came before. The first challenge astronomers faced was determining distances to celestial objects. Without knowing how far away something is, its true size cannot be calculated. A small nearby object and a large distant object can appear identical in the sky, and distinguishing between them requires independent distance measurements. For stars within our galaxy, the method of parallax provides direct geometric distances. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant stars, and the amount of this shift reveals the star's distance through simple trigonometry. But parallax becomes unmeasurably small for objects beyond a few thousand light years, requiring alternative methods for greater distances. The breakthrough that enabled extragalactic distance measurements came from the study of Cepheid variable stars. These pulsating stars brighten and dim with regular periods ranging from days to months, and in 1912, Henrietta Swan Leavitt discovered a crucial relationship between a Cepheid's period and its intrinsic luminosity. Longer period Cepheids are intrinsically brighter than shorter period ones, following a precise mathematical relationship. By measuring a Cepheid's period, astronomers could determine its true brightness, and by comparing this to its apparent brightness in the sky, they could calculate its distance. Cepheid variables enabled Edwin Hubble to measure the distance to the Andromeda Galaxy in 1924, establishing that galaxies existed beyond the Milky Way. Subsequent Cepheid observations extended the distance led to nearby galaxy clusters, though the method becomes impractical for distances beyond a few tens of millions of light years, where individual stars can no longer be resolved. For greater distances, astronomers developed additional techniques, including the use of Type Ia supernovae as standard candles. These stellar explosions occur when white dwarf stars exceed a critical mass, triggering thermonuclear detonation with remarkably consistent peak luminosity. By measuring a Type Ia supernova's apparent brightness, astronomers can determine the distance to its host galaxy even across billions of light-years. But measuring individual distances, while essential, was not sufficient for mapping large-scale structure. What astronomers needed was a method for determining distances to millions of galaxies efficiently, without waiting for rare supernova events or resolving individual stars. The solution came from redshift, the stretching of light wavelengths caused by cosmic expansion. In 1929, Hubble combined his distance measurements with observations of galaxy spectra to establish that more distant galaxies exhibited greater redshifts, a relationship now known as Hubble's law. This meant that redshift could serve as a proxy for distance, allowing astronomers to estimate how far away a galaxy lies simply by measuring the shift in its spectral lines. Spectroscopy, the analysis of light's component wavelengths, became the key to mapping the universe in 3 dimensions. Every galaxy's spectrum contains absorption and emission lines at specific wavelengths, corresponding to the elements present in its stars and gas. When these lines appear shifted toward longer wavelengths compared to laboratory measurements, the shift directly indicates the galaxy's recession velocity and, through Hubble's law, its distance. Early spectroscopic surveys were laborious, requiring individual observations of each galaxy with photographic plates that had to be manually measured. A single galaxy's redshift might require hours of telescope time, limiting surveys to a few thousand objects at most. The transformation began with the development of digital detectors in the 1970s. Charge-coupled devices, originally developed for video cameras, proved far more sensitive than photographic plates and produced data that could be processed by computers. When applied to astronomical spectroscopy, CCDS enabled faster and more accurate redshift measurements, opening the possibility of surveying tens of thousands of galaxies rather than mere hundreds. The next leap came from multiplexing, the ability to observe multiple objects simultaneously. Traditional spectroscopy examined one object at a time, but new instruments used fiber optics to collect light from hundreds of galaxies at once, feeding their light to a single spectrograph. The 2-degree field instrument on the Anglo-Australian telescope could observe 400 galaxies simultaneously, completing in a single night what would have taken months with previous technology. The Sloan Digital Sky Survey took this approach further, using a plate drilled with hundreds of holes, each positioned to align with a target galaxy and fitted with an optical fiber that carried its light to the spectrograph. These technological advances enabled surveys of unprecedented scale. The 2-degree field galaxy redshift survey mapped over 220,000 galaxies by 2003, revealing the cosmic web structure across a volume extending approximately 2 billion light-years. The Sloan Digital Sky Survey surpassed this achievement, mapping over 1 million galaxies in its first decade of operation and continuing to expand its coverage through subsequent phases. Each survey revealed structures larger than any previously known, pushing the boundaries of cosmic cartography. But optical redshift surveys face inherent limitations. They can only detect galaxies that emit or reflect detectable amounts of visible light, potentially missing populations of dim or obscured objects. They're also fundamentally limited by the speed at which spectra can be obtained, even with multiplexing technology. To map the most distant structures, astronomers turned to alternative tracers that could be detected across greater volumes of space. Quasars provided one such tracer. These extraordinarily luminous objects, powered by supermassive black holes consuming surrounding matter, can be seen across most of the observable universe. A single quasar can outshine its entire host galaxy by factors of hundreds, making it visible at distances where ordinary galaxies would be too faint to detect. Surveys like the Sloan Digital Sky Survey catalogued hundreds of thousands of quasars, mapping their distribution across billions of light-years. The discovery of the Huge Large Quasar Group in 2013 demonstrated that quasars trace structures spanning billions of light-years, concentrations of matter too large to explain through conventional models of structure formation. Gamma-ray bursts offered another window into cosmic structure at extreme distances. These brief but intense flashes of gamma radiation, lasting from milliseconds to several minutes, are the most energetic events in the universe. They occur when massive stars collapse to form black holes, or when neutron stars merge, releasing more energy in seconds than the Sun will emit in its entire lifetime. Because gamma-ray bursts are so energetic, they can be detected across the entire observable universe, providing distance markers in regions too remote for optical surveys to reach. The detection of gamma-ray bursts required space-based observatories, as Earth's atmosphere absorbs gamma radiation. The Compton Gamma Ray Observatory, launched in 1991, detected over 2,000 bursts during its 9-year mission, establishing that they were distributed uniformly across the sky and therefore originated at cosmological distances. Subsequent missions, including the Swift Observatory, launched in 2004, and the Fermi Gamma Ray Space Telescope, launched in 2008, provided more precise positions and enabled rapid follow-up observations to determine burst distances through spectroscopy of their afterglows. It was through analysis of gamma-ray burst distributions that the Hercules Corona Borealis Great Wall was discovered. In 2013, astronomers Istvan Horvath, John Hakila, and Zsolt Bagoli analysed the angular positions and distances of gamma-ray bursts detected over several years. They identified a statistically significant concentration of bursts in a region spanning approximately 45 degrees of sky in the direction of the constellations Hercules and Corona Borealis. The bursts in this concentration shared similar redshifts, indicating that they occurred at similar distances and therefore traced an underlying structure of immense proportions. The estimated size of this structure, approximately 10 billion light-years, exceeded all previous discoveries and approached the theoretical limits of what should be possible in the observable universe. Its detection relied not on counting individual galaxies, but on recognizing a pattern in the distribution of rare, extremely energetic events. This indirect method introduced uncertainties that continue to be debated, but subsequent analyses have supported the structure's existence, establishing it as the largest known concentration of matter in the cosmos. The Hercules Corona Borealis Great Wall defies easy comprehension. At an estimated 10 billion light-years in length, it spans approximately 1/9 of the observable universe's diameter. Light travelling from one end of this structure to the other would require 10 billion years to complete the journey, a duration approaching the age of the universe itself. No object created by human hands, no planetary system, no galaxy, no cluster of galaxies comes close to this scale. To understand what such a measurement means requires confronting the nature of cosmic distances and the expansion of space itself. A light-year is defined as the distance light travels in 1 year, approximately 9.5 trillion kilometers. This unit was developed precisely because conventional measurements become unwieldy at astronomical scales. Expressing the distance to nearby stars in kilometers requires numbers with 13 or more digits, making comparison and calculation impractical. Light-years provide a more intuitive unit, one that connects distance to time in a way that reflects how we actually observe the universe. When we look at a star 100 light-years away, we see it as it existed 100 years ago, because that is how long its light took to reach us. This connection between distance and time becomes crucial when discussing structures spanning billions of light-years. The Hercules Corona Borealis Great Wall lies at a redshift corresponding to a look-back time of approximately 10 billion years. This means the light we observe from this structure left its source when the universe was only about 4 billion years old, roughly 1/3 of its current age. We are not seeing the structure as it exists today, but as it existed in the distant past, a frozen image from an earlier cosmic epoch. But the concept of distance itself becomes complicated at cosmological scales. When astronomers say the Hercules Corona Borealis Great Wall spans 10 billion light-years, they must specify what kind of distance they mean. Several different distance measures are used in cosmology, each appropriate for different purposes, and they can differ substantially for objects at high redshift. The look-back time distance corresponds to how long light has been travelling to reach us. For the Hercules Corona Borealis Great Wall, this is approximately 10 billion years, meaning light from this structure has been journeying through space for 10 billion years before arriving at our telescopes. However, because the universe has been expanding during this time, the structure was much closer to us when the light was emitted than it is now. The proper distance, which represents the actual spatial separation at the present moment, is significantly larger than the look-back time distance. For objects at the redshift of the Hercules Corona Borealis Great Wall, the current proper distance is roughly 18 billion light-years. This discrepancy arises from cosmic expansion. Space itself has been stretching during the billions of years that light from distant objects has been travelling toward us. The light was emitted when the universe was smaller, when galaxies were closer together, but during its journey, space expanded, carrying those galaxies farther away. By the time the light arrives, the source has receded to a much greater distance than the light actually travelled. This is why the observable universe has a radius of approximately 46 billion light-years, even though the universe is only 13.8 billion years old. Light has not travelled 46 billion light-years. Rather, the sources that emitted the oldest light we can see have been carried to that distance by cosmic expansion. Understanding the Hercules corona borealis. Great Wall's true extent requires accounting for these effects. The structure's observed angular size on the sky, combined with its redshift, allows astronomers to calculate both its size at the time the light was emitted, and its size today after billions of years of expansion. Both numbers are staggering. At the time of emission, the structure already spanned several billion light-years, making it enormous, even by the standards of the younger, smaller universe. Today, after continued expansion, its proper extent is even larger, though the structure itself is no longer directly observable, since we can only see it as it was 10 billion years ago. The challenge of comprehending such distances extends beyond mere arithmetic. Human intuition evolved to navigate environments measured in meters and kilometers, not light-years. We can visualize a mountain or a city, perhaps even a continent, but the distance from Earth to the Moon already exceeds direct experience. The distance to the Sun is roughly 400 times greater still. The distance to the nearest star is another 100,000 times larger, and the distance to the Hercules corona borealis Great Wall exceeds the distance to the nearest star by roughly another 2 billion times. Analogies can help bridge this conceptual gap, though they inevitably distort as much as they illuminate. If the Sun were reduced to the size of a grain of sand, approximately 1 millimeter in diameter, the nearest star would be another grain of sand about 25 kilometers away. At this scale, the Milky Way galaxy would be a disk of sand grains spanning about 1 million kilometers, roughly 3 times the distance from Earth to the Moon. The Hercules corona borealis Great Wall, at this same scale, would span roughly 600 billion kilometers, larger than the actual solar system by a factor of 10,000. The analogy breaks down precisely because no everyday object provides an adequate reference. Perhaps more instructive is considering what the existence of such a structure implies about the universe's organization. The Hercules corona borealis Great Wall is not a solid object with defined boundaries. It is a region of enhanced galaxy density, a concentration of matter embedded within the cosmic web. Its 10 billion light-year extent represents the span over which this enhancement persists, the distance across which gamma-ray bursts occur more frequently than the cosmic average because more galaxies exist to host them. Within this vast region, individual galaxy clusters remain separated by tens of millions of light-years. The structure is not dense by everyday standards. It is merely denser than the surrounding voids. If you could somehow travel through the Hercules corona borealis Great Wall, you would pass through mostly empty space, with galaxies appearing as isolated islands separated by gulfs of near-perfect vacuum. The enhanced density manifests as a greater number of islands per unit volume, not as any approach to continuous matter. This perspective reveals something important about cosmic structure. At the largest scales, the universe is organized by relative abundance rather than by solid boundaries. A great wall is defined not by what it contains, but by how it compares to its surroundings. Remove the voids, and the wall would cease to be distinguishable. The structure exists only in contrast to regions of lower density, a pattern rather than an object in the conventional sense. Yet this pattern has physical reality. The galaxies within the Hercules corona borealis Great Wall are not randomly distributed. They trace underlying concentrations of dark matter that gravitationally attract both ordinary matter and light. The gamma-ray bursts that reveal the structure occur in galaxies within this concentration, their distribution reflecting the enhanced star formation and stellar death rates in regions of higher density. The pattern may be subtle when viewed locally, but it becomes unmistakable when millions of light-years are considered together. The question of whether such a vast structure constitutes a single coherent entity remains debated. Unlike a galaxy cluster, which is gravitationally bound and will persist indefinitely, the Hercules corona borealis Great Wall is too large to be held together by gravity. Cosmic expansion is pulling its component parts apart, and over tens of billions of years, the enhancement will likely disperse. The structure exists as a recognizable pattern today, but it is transient on cosmological timescales, a momentary concentration that will eventually fade into the cosmic average. This impermanence does not diminish the structure's significance. It demonstrates that the universe can produce correlations across distances previously thought impossible, that the seeds planted in the early universe can manifest as patterns spanning significant fractions of the observable cosmos. Understanding how such patterns arise and whether they are consistent with current cosmological models requires examining how the structure was actually detected and measured. The Hercules Corona Borealis Great Wall was not discovered by counting galaxies or mapping their positions in three-dimensional space. It was found through an entirely different method, one that relied on the distribution of gamma-ray bursts across the sky. These brief, intense flashes of high-energy radiation serve as markers of cosmic structure, tracing the locations of galaxies too distant to observe through conventional surveys. The technique that revealed the largest known structure in the universe depended on recognizing patterns in some of the most violent events the cosmos produces. Gamma-ray bursts are the most energetic explosions observed since the Big Bang itself. A single burst can release more energy in a few seconds than the Sun will emit over its entire 10 billion year lifetime. This energy emerges primarily as gamma rays, the highest energy form of electromagnetic radiation, with photons millions to billions of times more energetic than visible light. The bursts are so luminous that they can be detected across the entire observable universe, providing distance markers in regions far beyond the reach of optical galaxy surveys. The origin of gamma-ray bursts remained mysterious for decades after their discovery. They were first detected in the late 1960s by the Vela satellites, a series of spacecraft designed to monitor compliance with the Nuclear Test Ban Treaty by detecting gamma-ray signatures of nuclear explosions in space. Instead of treaty violations, the satellites detected bursts of gamma radiation coming from deep space, events that bore no resemblance to any known nuclear or terrestrial phenomenon. The discovery was classified initially, then published in 1973, launching a scientific puzzle that would take another quarter-century to resolve. Early hypotheses proposed that gamma-ray bursts originated within our galaxy, perhaps from nearby neutron stars or other compact objects. If this were true, the bursts would appear concentrated toward the Milky Way's disk and centre, where most galactic objects reside. But as more bursts were detected, their distribution proved remarkably uniform, scattered evenly across the entire sky, with no preference for the galactic plane. This isotropy suggested that gamma-ray bursts either came from a spherical halo surrounding our galaxy, or from cosmological distances, where the universe's large-scale homogeneity would produce the observed uniform distribution. The breakthrough came in 1997, when the Beppo-Sachs satellite detected a gamma-ray burst and quickly transmitted its position to ground-based telescopes. Within hours, astronomers identified a fading optical counterpart at the burst's location, and spectroscopic observations revealed absorption lines at a redshift of approximately 0.835. This placed the burst at a distance of roughly 6 billion light-years, confirming that gamma-ray bursts were indeed cosmological events of almost incomprehensible power. Subsequent observations established that gamma-ray bursts fall into two main categories based on their duration. Long bursts, lasting more than 2 seconds, are associated with the collapse of massive stars at the end of their lives. When a star more than roughly 25 times the Sun's mass exhausts its nuclear fuel, its core collapses directly to a black hole, and the infalling material forms an accretion disk that launches relativistic jets along the star's rotation axis. These jets punch through the stellar envelope and produce the observed gamma-ray emission through internal shocks and interactions with surrounding material. Long gamma-ray bursts therefore trace regions of active star formation, occurring preferentially in galaxies where massive stars are being born and dying. Short bursts lasting less than 2 seconds have a different origin. They are now understood to result from the merger of compact objects, either two neutron stars or a neutron star and a black hole. These binary systems spiral together over millions or billions of years as gravitational wave emission drains their orbital energy. When they finally merge, the violent collision produces a brief but intense flash of gamma rays, along with gravitational waves that have been directly detected by observatories like LIGO and Virgo. Short gamma-ray bursts can occur in any type of galaxy, including those with little ongoing star formation, since the progenitor systems may be very old. Both types of gamma-ray bursts serve as traces of cosmic structure because they occur in galaxies. The rate of long bursts reflects the cosmic star formation rate, which varies with both time and location. Regions with more galaxies produce more massive stars, which in turn produce more gamma-ray bursts when those stars die. By mapping the distribution of gamma-ray bursts across the sky and measuring their distances through redshift observations, astronomers can infer the underlying distribution of matter even in regions too distant for direct galaxy surveys. The analysis that revealed the Hercules Corona Borealis Great Wall was conducted by Istvan Horvath, John Hakila, and Zsolt Bagoli, who examined the angular positions and redshifts of gamma-ray bursts detected over several years. Their approach involved searching for statistically significant concentrations of bursts in both position and distance, regions where more bursts occurred than would be expected from a uniform random distribution. The method required careful statistical analysis because the sample of gamma-ray bursts with measured redshifts was limited, numbering in the hundreds rather than the millions of galaxies available in optical surveys. What they found was a concentration of gamma-ray bursts spanning approximately 45 degrees of sky in the direction of the constellations Hercules and Corona Borealis. The bursts in this concentration shared similar redshifts, clustering around a value corresponding to a look-back time of approximately 10 billion years. The probability of such a concentration arising by chance from a uniform distribution was calculated to be extremely low, suggesting that the bursts traced a real underlying structure rather than a statistical fluctuation. The angular extent of the concentration combined with its distance implied a physical size of approximately 10 billion light-years. This number immediately raised questions because it exceeded the size of any previously known structure by a substantial margin. The Sloan Great Wall, previously the largest known structure, spans roughly 1.4 billion light-years. The Hercules Corona Borealis Great Wall appeared to be more than 7 times larger, a difference too great to dismiss as measurement uncertainty. Subsequent analyses have both supported and refined the original discovery. Additional gamma-ray burst data have been incorporated, and alternative statistical methods have been applied to test the robustness of the detection. While some researchers have questioned whether the structure is as large and coherent as initially claimed, the consensus has moved toward accepting its existence, though debates about its precise extent continue. The use of gamma-ray bursts as structural probes introduces uncertainties that would not affect optical galaxy surveys. The sample size is small, with only a few hundred bursts having measured redshifts in the relevant distance range. The relationship between gamma-ray burst rates and underlying galaxy density depends on factors like star formation history and metallicity that vary across cosmic time. And the statistical methods used to identify overdensities must account for selection effects in how bursts are detected and followed up. Despite these uncertainties, the gamma-ray burst method offers unique advantages. Because bursts are so luminous, they can probe distances where galaxies are too faint to detect individually. They provide a way to trace structure in the distant universe that complements and extends optical surveys, and their distribution across the sky can reveal patterns that might be missed by surveys covering limited areas. The discovery of the Hercules Corona Borealis Great Wall through gamma-ray burst mapping represents a triumph of indirect observation, finding the largest known structure not by seeing it directly, but by recognizing the pattern it imprints on some of the universe's most extreme events. This approach continues to be refined as more bursts are detected and our understanding of their origins improves. The existence of the Hercules Corona Borealis Great Wall poses a fundamental challenge to one of cosmology's core assumptions. The cosmological principle, a foundational tenet that has guided our understanding of the universe for nearly a century, asserts that on sufficiently large scales, the universe is homogeneous and isotropic. Homogeneity means that matter is distributed evenly throughout space, with no preferred locations or special regions. Isotropy means the universe looks the same in all directions, with no privileged orientations. A structure spanning 10 billion light-years appears to violate both aspects of this principle, forcing astronomers to reconsider what we mean by sufficiently large scales. The cosmological principle emerged from philosophical and observational considerations in the early 20th century. Einstein adopted a version of it when developing general relativity, assuming that the universe was static, homogeneous, and isotropic to simplify his equations. Although the static assumption was quickly abandoned after Hubble's discovery of cosmic expansion, the homogeneity and isotropy assumptions remained central to cosmological models. They were not merely mathematical conveniences but reflected a Copernican insight. Earth occupies no special place in the cosmos, and by extension, no location in the universe should be fundamentally different from any other. Observations initially supported this assumption. The cosmic microwave background radiation, the afterglow of the Big Bang detected in 1964, proved remarkably uniform across the sky. Temperature variations of only 1 part in 100,000 indicated that the early universe was extraordinarily homogeneous, with matter distributed almost perfectly evenly throughout space. As this primordial soup cooled and condensed into structures, some inhomogeneity was expected, but the overall smoothness of the cosmic microwave background suggested that large-scale homogeneity should persist. Galaxy surveys also appeared consistent with the cosmological principle, at least initially. While galaxies cluster on scales of millions of light-years, these clusters seem to be distributed randomly when viewed at larger scales. Statistical measures of galaxy clustering, such as the correlation function that quantifies how galaxy density varies with separation, showed that clustering strength decreased with distance. Beyond a few hundred million light-years, galaxies appeared to approach a uniform distribution, precisely as the cosmological principle predicted. But as surveys probed larger volumes, unexpected structures emerged. The discovery of the original Great Wall in 1989 revealed a concentration of galaxies spanning 500 million light-years, larger than many astronomers had anticipated. The Sloan Great Wall at 1.4 billion light-years pushed the scale of observed structures even higher, and the Huge Large Quasar Group, spanning 4 billion light-years, demonstrated that coherent structures existed at scales previously thought impossible. The cosmological principle does not specify exactly how large sufficiently large must be. Different analyses have proposed different homogeneity scales, the distance above which the universe should appear uniform. Some studies suggest homogeneity emerges at scales around 250 million light-years, while others argue for scales up to 1 billion light-years. The existence of structures several billion light-years in extent challenges even the most generous estimates, suggesting either that the homogeneity scale is much larger than previously thought, or that the cosmological principle requires modification. The Hercules Corona Borealis Great Wall represents the most extreme challenge yet. At 10 billion light-years, it spans approximately 1/9 of the observable universe's diameter. If we imagine dividing the observable universe into regions of this size, we would have fewer than 10 such regions. Finding a significant overdensity in one of these regions suggests that matter distribution at the largest observable scales is not homogeneous, but structured, with density varying substantially from place to place. This inhomogeneity has profound implications for cosmological models. The standard lambda CDM model, which describes a universe dominated by dark energy and cold dark matter, assumes the cosmological principle as a foundational input. The equations governing cosmic expansion, the predictions for structure formation, and the interpretation of observational data all depend on this assumption. If the universe is significantly inhomogeneous at large scales, these calculations may require revision. One possibility is that the observed structures are not as coherent as they appear. Galaxy surveys and gamma-ray burst distributions may be subject to selection effects and statistical fluctuations that create the appearance of large structures where none truly exist. The limited sample sizes, particularly for gamma-ray bursts with measured redshifts, introduce uncertainty that could be mistaken for genuine structure. Some researchers have argued that the Hercules Corona Borealis Great Wall and similar structures may be artifacts of incomplete data rather than real features of the cosmic matter distribution. However, multiple independent analyses using different datasets and methods have confirmed the existence of anomalously large structures. The consistency of these findings across different research groups and observational techniques suggests that the structures are real, even if their precise extents remain uncertain. The challenge they pose to the cosmological principle cannot be easily dismissed as observational error. Another possibility is that the homogeneity scale is simply larger than previously estimated. Perhaps the universe does become uniform at scales significantly greater than 10 billion light-years, but our observations have not yet probed volumes large enough to demonstrate this. The observable universe, with a diameter of approximately 93 billion light-years, is finite, and we cannot see beyond its boundaries. If homogeneity only emerges at scales comparable to, or larger than, the observable universe, we would have no way to confirm it through direct observation. This possibility is troubling because it renders the cosmological principle unfalsifiable with current data. A principle that cannot be tested against observations loses its scientific utility, becoming more a matter of faith than empirical fact. Cosmologists have generally assumed that the universe should appear homogeneous well within the observable volume, allowing the principle to be tested and confirmed. The discovery of structures approaching the observable universe's scale undermines this assumption. A more radical possibility is that the cosmological principle is simply wrong, that the universe is fundamentally inhomogeneous even at the larger scales. This would require rethinking much of modern cosmology, potentially invalidating assumptions built into everything from measurements of cosmic expansion to estimates of the universe's age and composition. The implications would be far-reaching, affecting not only theoretical models, but also the interpretation of nearly all cosmological observations. Some researchers have proposed that we might live in a special region of the universe, a local void or overdensity that creates the appearance of anomalous structures. If our cosmic neighbourhood is atypical, the structures we observe might not represent the universe as a whole. This explanation has the uncomfortable consequence of placing us in a privileged location, contradicting the Copernican principle that motivated the cosmological principle in the first place. The tension between observed structures and the cosmological principle remains unresolved. Current data are insufficient to definitively confirm or refute the principle at the larger scales. Future surveys, mapping billions of galaxies across most of the sky, may provide the statistical power needed to determine whether structures like the Hercules Corona Borealis Great Wall are exceptional flukes or representatives of a genuinely inhomogeneous cosmos. Until then, the largest known structure stands as a challenge to our most basic assumptions about the universe's organization. The sheer size of the Hercules Corona Borealis Great Wall raises a question that cuts to the heart of cosmological theory. How could something so vast have formed in a universe only 13.8 billion years old? The standard model of structure formation relies on gravity to amplify small initial density fluctuations into the galaxies, clusters, and cosmic web we observe today. But gravity works slowly, and the time available since the Big Bang appears insufficient to build a coherent structure spanning 10 billion light-years. This tension between observation and theory represents one of the most significant puzzles in modern cosmology. Structure formation in the universe proceeds through a process called gravitational instability. In the early universe, matter was distributed almost uniformly, but tiny fluctuations existed, regions where the density was slightly higher or lower than average. These fluctuations, seeded during the inflationary epoch and imprinted on the cosmic microwave background, provided the starting point for all subsequent structure. Regions with slightly higher density exerted slightly stronger gravitational attraction, drawing in surrounding matter and becoming denser still. Over time, this positive feedback amplified the initial fluctuations, eventually producing the galaxies and clusters we observe today. The rate at which structures grow depends on several factors. The strength of gravitational attraction, determined by the density of matter in the universe, sets the basic timescale. The expansion of the universe works against gravitational collapse, stretching space and diluting matter before it can fully condense, and the properties of dark matter, which dominates the gravitational dynamics of structure formation, determine how fluctuations at different scales evolve. In the standard lambda-CDM model, dark matter consists of cold particles that move slowly compared to the speed of light. This coldness allows dark matter to clump efficiently on small scales, forming the halos that host galaxies and galaxy clusters. Ordinary matter, initially prevented from collapsing by radiation pressure, falls into these dark matter halos once the universe cools sufficiently, condensing into stars and galaxies. The process proceeds hierarchically, with small structures forming first and merging over time into larger ones. This hierarchical model successfully reproduces many observed properties of the universe. Computer simulations based on lambda CDM produce cosmic webs with statistical properties matching galaxy surveys. They correctly predict the abundance of galaxy clusters as a function of mass and redshift. They reproduce the clustering patterns observed in the cosmic microwave background and the distribution of matter inferred from gravitational lensing. By almost any measure, the lambda CDM model is remarkably successful at describing cosmic structure. But the model also makes predictions about the maximum size of structures that can form. Because gravity propagates at the speed of light, regions separated by more than the cosmic horizon at any given time cannot gravitationally interact. The horizon grows as the universe ages, expanding at roughly the speed of light and encompassing ever larger volumes. Structures can only become coherent once the regions that will comprise them have come into causal contact, meaning light and gravity have had time to travel between them. This constraint implies a maximum scale for gravitationally bound structures. At the present epoch, the cosmic horizon encompasses the entire observable universe, but in the past it was much smaller. Structures that exist today must have been within each other's horizons early enough for gravity to act over cosmic time. Detailed calculations suggest that coherent structures should not exceed a few hundred megaparsecs, roughly 1 billion light-years in the current universe. Larger concentrations might exist as statistical enhancements, regions where the random distribution of matter happens to produce above-average density, but they should not represent gravitationally coherent structures. The Hercules Corona Borealis Great Wall, at 10 billion light-years, vastly exceeds this theoretical limit. Its existence implies either that the structure is not gravitationally coherent in the usual sense, or that something is missing from the standard model of structure formation. Neither possibility is easy to accept, and both have been explored in the scientific literature. One interpretation holds that the Hercules Corona Borealis Great Wall is not a single structure, but rather a chance alignment of multiple smaller structures along our line of sight. Projection effects can create the appearance of large-scale correlations where none truly exist. If several independent walls and filaments happen to lie at similar redshifts in the same region of sky, their combined gamma-ray burst populations would produce an apparent overdensity spanning the entire region. Statistical analyses have attempted to assess the probability of such chance alignments. The original discovery paper calculated that the observed concentration was highly unlikely to arise from random fluctuations in a uniform distribution. Subsequent analyses have both supported and challenged this conclusion, with different statistical methods yielding different significance estimates. The debate reflects the difficulty of drawing conclusions from limited data, particularly when the structures being sought are comparable in size to the survey volume itself. Another possibility is that the initial conditions for structure formation were different from what the standard model assumes. The lambda CDM model derives its initial fluctuation spectrum from inflation, the brief period of exponential expansion in the early universe that stretched quantum fluctuations to cosmic scales. Inflation predicts a nearly scale-invariant spectrum, meaning fluctuations have similar amplitude across a wide range of sizes. This prediction matches observations of the cosmic microwave background with remarkable precision, lending strong support to the inflationary paradigm. However, the cosmic microwave background probes fluctuations at a specific epoch, roughly 380,000 years after the Big Bang, when the universe became transparent to radiation. Fluctuations at larger scales, corresponding to structures that would not become observable until much later, are less well constrained. If the primordial fluctuation spectrum departed from scale invariance at very large scales, enhanced initial fluctuations could have seeded structures larger than the standard model predicts. Some inflationary models naturally produce such features. Inflation might have occurred in multiple stages, with brief interruptions that left imprints in the fluctuation spectrum. The inflaton field, which drove the exponential expansion, might have had features in its potential energy landscape that created localized enhancements in the fluctuation amplitude. These possibilities remain speculative, but they illustrate how modifications to the standard inflationary scenario could potentially accommodate anomalously large structures. A more radical possibility involves modifications to gravity itself. General relativity has been tested extensively on scales from laboratory experiments to the solar system, but its behavior at cosmological scales is less directly constrained. modified gravity theories, developed primarily to explain cosmic acceleration without invoking dark energy, might also affect structure formation in ways that allow larger coherent structures to develop. These theories remain controversial and face significant observational challenges, but they represent an active area of research. The formation mystery surrounding the Hercules Corona Borealis Great Wall remains unsolved. Its existence pushes against the boundaries of current theoretical understanding, suggesting either that our models are incomplete or that the structure itself is not what it appears to be. Resolving this question will require both better observations to characterize the structure more precisely and theoretical advances to understand what its existence implies about cosmic evolution. The Hercules Corona Borealis Great Wall holds the current record for the largest known structure, but it does not stand alone. The universe contains other enormous concentrations of matter that similarly challenge our understanding of cosmic evolution. The Sloan Great Wall, the Huge Large Quasar Group, and the Giant Arc each represent independent discoveries of structures spanning billions of light years. Together they suggest that anomalously large structures may not be rare exceptions, but rather common features of the cosmos at its grandest scales. The Sloan Great Wall was discovered in 2003 through analysis of data from the Sloan Digital Sky Survey. Unlike the Hercules Corona Borealis Great Wall, which was detected through gamma-ray burst distributions, the Sloan Great Wall was mapped directly by measuring the positions and redshifts of individual galaxies. The structure appears as an elongated concentration of galaxies approximately 1.4 billion light-years in length, located at a distance of roughly 1 billion light-years from Earth. It contains several superclusters connected by dense filaments, forming a coherent wall that stretches across a significant portion of the survey volume. At the time of its discovery, the Sloan Great Wall was the largest known structure in the universe, exceeding the original Great Wall discovered in 1989 by nearly a factor of 3. Its existence demonstrated that the cosmic web contained features far larger than individual superclusters, concentrations of matter that challenged prevailing estimates of the homogeneity scale. The Sloan Great Wall remained the record holder for nearly a decade before being surpassed by structures detected at greater distances. The Huge Large Quasar Group, identified in 2013, represented the next major step in the progression toward larger structures. Quasars are extremely luminous active galactic nuclei powered by supermassive black holes, visible across most of the observable universe due to their extraordinary brightness. By mapping the positions and distances of quasars, astronomers can trace the distribution of matter at epochs when the universe was much younger than it is today. The Huge Large Quasar Group consists of 73 quasars distributed across a region approximately 4 billion light-years in extent. It lies at a redshift corresponding to a look-back time of roughly 9 billion years, meaning we observe it as it existed when the universe was less than 5 billion years old. The structure's size and coherence were unexpected, as standard models predicted that quasar distribution should appear random at such scales. Its discovery prompted renewed debate about the cosmological principle and the maximum size of cosmic structures. Roger Close, the lead author of the discovery paper, noted that the Huge Large Quasar Group exceeded the theoretical homogeneity scale by a factor of several. If the cosmological principle held, structures of this size should not exist. The finding was met with both interest and skepticism, with some researchers questioning whether the quasar grouping represented a genuine physical structure or a statistical fluctuation in an otherwise random distribution. Subsequent analyses have generally supported its reality, though debates about its precise extent and significance continue. The Giant Arc, announced in 2021, added another entry to the catalogue of impossibly large structures. This feature was discovered through analysis of magnesium absorption in the spectra of distant quasars. When light from a quasar passes through intervening gas, specific wavelengths are absorbed depending on the elements present. By mapping these absorption features across many quasar sightlines, astronomers can reconstruct the distribution of gas in the foreground universe. The Giant Arc appears as a crescent-shaped concentration of matter spanning approximately 3.3 billion light-years. It lies at a redshift of approximately 0.8, corresponding to a look-back time of roughly 7 billion years. The structure's distinctive curved shape distinguishes it from the more linear walls and filaments typically observed in the cosmic web. Its discovery, like those before it, raised questions about how such an enormous coherent feature could form. Alexia Lopez, who led the team that discovered the giant arc, presented the findings at a meeting of the American Astronomical Society. She emphasized that the structure's size challenged standard cosmological models, adding to the growing list of features that seem too large to exist. The giant arc lies relatively close to the huge large quasar group on the sky, raising questions about whether the two structures might be related or part of an even larger complex. These discoveries reveal a pattern. As observational capabilities have improved, allowing astronomers to map larger volumes of the universe with greater precision, progressively larger structures have emerged. Each new record holder has challenged existing theoretical limits, forcing revisions in estimates of the homogeneity scale and prompting questions about the adequacy of current models. The progression from the original Great Wall at 500 million light-years to the Hercules Corona Borealis Great Wall at 10 billion light-years represents an increase of a factor of 20 in just 3 decades of observation. Whether this progression will continue remains uncertain. The observable universe has a finite size, approximately 93 billion light-years in diameter, setting an absolute upper limit on the structures we can detect. As surveys probe ever larger volumes, approaching the entire observable cosmos, the opportunity for discovering even larger structures may be exhausted. Alternatively, the largest structures may already have been found, with future surveys filling in details rather than revealing new record holders. The relationship between these giant structures also remains poorly understood. The Hercules Corona Borealis Great Wall, the huge large quasar group and the giant arc all lie at substantial distances, observable as they existed billions of years ago. Whether they represent independent concentrations or connected parts of even larger complexes cannot be determined from current data. The cosmic web is three-dimensional, and apparent proximity on the sky does not necessarily indicate physical association. What seems clear is that the universe contains structures at scales previously thought impossible. Whether these structures represent failures of current theory, limitations of current observation, or genuinely new phenomena requiring new physics, they demand explanation. The existence of multiple independently discovered giant structures strengthens the case that something significant is being revealed, something that goes beyond statistical fluctuation or observational artifact. Comparative studies of these structures have begun to reveal common properties. They tend to be elongated rather than spherical, consistent with the filamentary nature of the cosmic web. They contain enhanced densities of galaxies, quasars, or gamma-ray bursts compared to surrounding regions, and they lie at redshifts corresponding to epochs when the universe was younger and denser, when structure formation was more active. These similarities suggest that giant structures may be extreme manifestations of the same physical processes that produce smaller features, amplified by exceptional initial conditions or favourable geometries. Understanding the competing giants of the cosmic web requires both observational and theoretical advances. Larger surveys mapping more of the sky to greater depths will provide better statistics on the abundance and properties of giant structures. Improved simulations incorporating more realistic physics may reveal whether such structures can form within the standard cosmological framework, and new theoretical ideas may provide alternative explanations for observations that current models struggle to accommodate. The structures we observe in the universe, from individual galaxies to walls spanning billions of light-years, represent only a fraction of the total mass present. Ordinary matter, the atoms and molecules that compose stars, planets, and living beings, accounts for roughly 5% of the universe's total energy content. The remaining 95% consists of dark matter and dark energy, two components that have never been directly observed but whose existence is inferred from their gravitational effects. Understanding the largest structures in the universe requires understanding dark matter, the invisible scaffolding upon which the cosmic web is built. The evidence for dark matter emerged gradually over decades of observation. Fritz Zwicky's 1933 measurements of galaxy velocities in the Coma cluster provided the first hint, revealing that the cluster contained far more mass than its visible galaxies could account for. Zwicky's finding was largely ignored for decades, dismissed as measurement error or an anomaly specific to one cluster, but in the 1970s, astronomer Vera Rubin and her collaborator Kent Ford obtained data that could not be so easily dismissed. Rubin and Ford measured the rotation curves of spiral galaxies, plotting how orbital velocity varied with distance from the galactic center. According to Newtonian gravity, stars in the outer regions of a galaxy should orbit more slowly than those near the center, just as outer planets in our solar system orbit more slowly than inner ones. The visible mass of a galaxy is concentrated in its center, so gravitational attraction should weaken with distance, producing declining rotation curves in the outer regions. What Rubin and Ford observed was dramatically different. The rotation curves of spiral galaxies remained flat or even rose slightly in their outer regions, indicating that stars at large distances from the center orbited just as fast as those closer in. This could only be explained if galaxies contained substantial amounts of mass beyond their visible boundaries, mass that extended far into their outer halos and provided additional gravitational attraction to maintain high orbital velocities. The pattern proved universal. Every spiral galaxy examined showed the same flat rotation curves, indicating that dark matter halos were not exceptional, but ubiquitous. Further evidence came from gravitational lensing, the bending of light by massive objects predicted by general relativity. Galaxy clusters bend the light from more distant galaxies, distorting their images in ways that depend on the cluster's total mass. Lensing measurements consistently indicated masses far exceeding what visible matter could provide, confirming that dark matter dominates the mass budget of large structures. The cosmic microwave background provided yet another line of evidence. The tiny temperature fluctuations in this primordial radiation reflect density variations in the early universe, variations that seeded all subsequent structure. The statistical properties of these fluctuations depend on the relative amounts of ordinary matter, dark matter, and dark energy in the universe. Detailed analysis of cosmic microwave background data from satellites like COBE-WMAP and Planck has determined that dark matter comprises approximately 27% of the universe's total energy content, roughly 5 times more than ordinary matter. Despite overwhelming evidence for its existence, the nature of dark matter remains unknown. It does not emit, absorb, or scatter light, making it invisible to telescopes operating at any wavelength. It does not interact through the electromagnetic force, which governs the behavior of charged particles and produces the light we observe. It does not participate in nuclear reactions, ruling out ordinary atomic matter in any form. Dark matter interacts with other matter only through gravity, and possibly through the weak nuclear force, making direct detection extraordinarily challenging. Numerous experiments have attempted to detect dark matter particles directly. Deep underground detectors, shielded from cosmic rays and other backgrounds, search for the rare interactions that might occur when dark matter particles collide with atomic nuclei. So far, no confirmed detection has been made, though several experiments have reported tantalizing hints that remain unverified. The failure to detect dark matter directly has constrained its possible properties, ruling out many theoretical candidates while leaving others viable. The leading theoretical candidate for dark matter is a class of particles called WIMPs, weakly interacting massive particles. WIMPs would have been produced in the hot early universe and would interact through the weak nuclear force, providing a potential detection signature. Their predicted abundance matches the observed dark matter density remarkably well, a coincidence known as the WIMP miracle that has motivated decades of experimental searches. However, the continued absence of WIMP detections has led some researchers to consider alternative candidates. Axions represent another possibility. These hypothetical particles were originally proposed to solve a problem in quantum chromodynamics, the theory of the strong nuclear force, but they would also have properties suitable for dark matter. Axions would be extremely light, far lighter than WIMPs, and would interact even more weakly with ordinary matter. Specialized experiments using strong magnetic fields to convert axions into detectable photons are underway, though no detection has yet been confirmed. More exotic possibilities include primordial black holes that formed in the early universe rather than from stellar collapse. If primordial black holes exist in sufficient numbers and with appropriate masses, they could account for some or all of the dark matter. Observational constraints from gravitational lensing and other techniques have ruled out primordial black holes over certain mass ranges, but windows remain where they could contribute significantly to the dark matter budget. Regardless of its particle nature, dark matter's role in structure formation is well understood. Because dark matter does not interact electromagnetically, it was not affected by the radiation that filled the early universe and prevented ordinary matter from collapsing. Dark matter began forming structures much earlier than ordinary matter, creating gravitational potential wells that ordinary matter later fell into. The distribution of dark matter today traces the cosmic web, with dense halos surrounding galaxies and clusters connected by filaments of more diffuse dark matter. Computer simulations of structure formation model dark matter as the primary driver of gravitational evolution. The Millennium simulation and its successors track billions of dark matter particles as they interact gravitationally over cosmic time. The resulting structures reproduce the observed cosmic web with remarkable fidelity, demonstrating that dark matter provides the gravitational framework upon which visible structure is built. Without dark matter, the universe would look dramatically different, with far less clustering and no galaxies resembling those we observe. The largest structures in the universe, including the Hercules Corona Borealis Great Wall, are fundamentally dark matter structures. The galaxies and gamma-ray bursts that reveal their presence trace underlying concentrations of dark matter that provide the gravitational glue holding them together. Understanding these structures requires understanding dark matter, yet dark matter remains one of the deepest mysteries in physics. The invisible mass that shapes the cosmos on its grandest scales has never been seen, touched, or identified with any known particle. It is known only through its effects, a shadow presence inferred from the motions of stars and the bending of light. For every great wall of galaxies stretching across billions of light years, there exists a counterpart of equal significance but opposite character. Cosmic voids are the vast empty regions between the filaments and walls of the cosmic web, spanning hundreds of millions of light years with remarkably few galaxies within their boundaries. These underdense regions occupy the majority of the universe's volume, yet they receive far less attention than the dense concentrations that define structure. Understanding the larger structures requires understanding the voids that surround them, the emptiness that gives the cosmic web its definition. Voids were among the first large-scale features recognized in galaxy surveys. The Boötes void, discovered in 1981, was one of the earliest identified, a roughly spherical region approximately 330 million light-years in diameter, containing only a handful of galaxies where hundreds would be expected. Its discovery challenged assumptions about the uniformity of galaxy distribution, demonstrating that the universe contained regions of extreme underdensity, as well as the clusters and walls that had previously attracted attention. The typical cosmic void spans between 100 and 300 million light-years, though larger voids have been identified as surveys have mapped greater volumes. The KBC void, named after the astronomers who characterized it, may extend up to 2 billion light-years across, encompassing our own local group and much of the nearby universe. If confirmed at this size, the KBC void would represent one of the largest coherent underdense regions known, with implications for how we interpret observations of cosmic expansion. Voids are not completely empty. They contain galaxies, though at densities far below the cosmic average. The galaxies found within voids tend to differ systematically from those in denser environments. Void galaxies are often smaller, bluer, and more actively forming stars than their counterparts in clusters and filaments. They have experienced fewer gravitational interactions and mergers, preserving characteristics that reflect earlier stages of galactic evolution. Studying void galaxies provides a window into how galaxies develop in isolation, free from the environmental influences that shape evolution in denser regions. The formation of voids follows naturally from gravitational instability. In the early universe, regions with slightly below average density exerted weaker gravitational attraction than their surroundings. Matter flowed out of these regions toward denser concentrations, amplifying the initial underdensity over time. As billions of years passed, the underdense regions expanded while the dense regions contracted, producing the sharp contrast between voids and walls observed today. Computer simulations reproduce void formation with the same fidelity they achieve for dense structures. Beginning with the nearly uniform matter distribution of the early universe, simulations show voids emerging as matter evacuates from underdense regions and accumulates along filaments and at cluster nodes. The statistical properties of simulated voids match observations remarkably well, including their size distribution, shapes, and the properties of galaxies within them. This agreement confirms that voids and dense structures are two aspects of the same physical process, gravitational evolution acting on primordial density fluctuations. The relationship between voids and great walls is intimate and necessary. A wall exists only in contrast to the voids on either side of it. Remove the voids, and the wall would cease to be distinguishable from its surroundings. The cosmic web's architecture depends on this contrast, the alternation of dense and empty regions that creates the network structure visible in galaxy surveys. Great walls like the Hercules Corona Borealis structure are defined as much by the voids that border them as by the galaxies they contain. This perspective suggests a different way of thinking about cosmic structure. Rather than focusing exclusively on the concentrations of matter that form walls and filaments, we might equally well describe the universe as a network of voids separated by thin sheets and threads of matter. The two descriptions are equivalent dual perspectives on the same underlying distribution. But emphasizing voids highlights an important point. Most of the universe's volume is nearly empty, and the structures we marvel at occupy only a small fraction of cosmic space. Voids also play an active role in cosmic evolution. They are not static regions of emptiness, but dynamic features that continue to grow as matter flows out of them. The expansion of voids pushes against the filaments and walls at their boundaries, contributing to the stretching of the cosmic web over time. This expansion is accelerated by dark energy, the mysterious component that drives the universe's accelerating expansion. Within voids, where the density of matter is lowest, dark energy's repulsive effect is least opposed by gravitational attraction, causing voids to expand faster than denser regions. The interplay between voids and dense structures may influence observations in subtle ways. Light travelling from distant galaxies to our telescopes must cross regions of varying density, passing through both voids and filaments along its path. The gravitational effects of these density variations can slightly alter the light's path and energy, affecting measurements of distances and redshifts. If our local region of the universe is embedded in a particularly large void, as some studies suggest, these effects could bias our observations of cosmic expansion, potentially contributing to the tension between different measurements of the expansion rate. The KBC void hypothesis proposes that the local group lies within an underdense region, extending roughly 2 billion light-years in all directions. If true, the reduced gravitational attraction within this void would cause our local measurements of cosmic expansion to differ from the global average. Galaxies we observe would be receding faster than they would in a region of average density, producing higher apparent expansion rates. This effect could partially explain why measurements of the Hubble constant using local distance indicators consistently yield higher values than those derived from the cosmic microwave background. The void hypothesis remains controversial. Some analyses support the existence of a large local underdensity, while others find no significant deviation from the cosmic average. The difficulty lies in measuring density variations on such large scales, where selection effects and systematic errors can easily produce spurious signals. Regardless of whether the KBC void exists at its proposed size, the hypothesis illustrates how voids can influence cosmological observations and interpretations. The largest voids, like the largest walls, approach scales that challenge the cosmological principle. If matter is distributed uniformly on sufficiently large scales, both overdense and underdense regions should average out, producing a smooth distribution when viewed from far enough away. The existence of voids spanning billions of light-years, like the existence of walls of similar extent, suggests that this averaging occurs only at scales approaching the observable universe itself, if it occurs at all. Voids and walls together constitute the cosmic web, the largest pattern of organization in the universe. Neither can be understood in isolation. Each defines and is defined by the other. The Hercules Corona Borealis Great Wall is remarkable, not only for its extent, but for the voids that must surround it. The vast empty regions that border a concentration spanning 10 billion light-years. Mapping these voids with the same precision as the walls themselves remains a challenge for future surveys, one that will complete our picture of structure at the universe's grandest scales. The seeds of the largest structures in the universe were planted in the first fraction of a second after the Big Bang. During a period known as cosmic inflation, the universe expanded exponentially, doubling in size roughly every 10 to the negative 34 seconds. This expansion was so rapid and so extreme that it stretched quantum fluctuations, the inherent uncertainty in energy and position at subatomic scales, to cosmic dimensions. These inflated quantum fluctuations became the density variations that gravity later amplified into galaxies, clusters, and the vast walls that span billions of light years. The Hercules Corona Borealis Great Wall, for all its immensity, traces its origin to events that occurred when the universe was younger than the time it takes light to cross a proton. Inflation was proposed in 1980 by physicist Alan Guth as a solution to several puzzles in standard Big Bang cosmology. The universe appeared far too uniform and geometrically flat to be explained by ordinary expansion from a hot, dense initial state. Regions on opposite sides of the observable universe, separated by distances too great for light to have travelled between them since the Big Bang, nonetheless exhibited nearly identical temperatures in the cosmic microwave background. This uniformity, known as the horizon problem, suggested that these regions had once been in contact, able to exchange energy and reach thermal equilibrium before being separated by expansion. Inflation solved this puzzle by proposing that the universe underwent a brief but extreme burst of expansion very early in its history. Before inflation, the region that would become our observable universe was small enough for all parts to be in causal contact, allowing equilibration to occur. Inflation then stretched this small uniform region to cosmic scales, carrying the uniformity to distances far beyond what light could traverse in ordinary expansion. The horizon problem dissolved because the seemingly disconnected regions had in fact been connected before inflation separated them. The flatness problem received a similar resolution. The geometry of the universe depends on its total energy density. Too much energy in the universe would be positively curved, eventually collapsing back on itself. Too little and it would be negatively curved, expanding forever at an ever-increasing rate. Only with a very specific critical density would the universe be geometrically flat, with parallel lines remaining parallel over arbitrarily large distances. Observations indicate that the universe is flat to remarkable precision, yet maintaining this flatness through billions of years of expansion requires extraordinarily fine-tuned initial conditions in standard cosmology. Inflation addressed this fine-tuning by recognizing that exponential expansion drives any initial geometry toward flatness. The rapid stretching dilutes it to negligible levels, just as inflating a balloon makes its surface appear progressively flatter. The observed flatness of the universe, rather than requiring improbable initial conditions, becomes a natural consequence of inflationary expansion. But inflation's most profound contribution concerns the origin of cosmic structure. Quantum mechanics dictates that empty space is not truly empty, but seethes with virtual particles and energy fluctuations appearing and disappearing on timescales governed by the uncertainty principle. Under normal conditions, these quantum fluctuations remain confined to subatomic scales, imperceptible to macroscopic observation. But during inflation, the exponential expansion stretched these fluctuations faster than they could oscillate, freezing them in place at progressively larger scales. By the time inflation ended, quantum fluctuations had been amplified to macroscopic dimensions, imprinted as tiny variations in the density of matter and energy throughout the expanding universe. These variations were small, roughly 1 part in 100,000, but they provided the seeds from which all structure would grow. Regions with slightly higher density would attract surrounding matter gravitationally, becoming denser still, while regions with slightly lower density would lose matter to their denser neighbours, becoming emptier. Over billions of years, this gravitational amplification transformed the nearly uniform post-inflationary universe into the cosmic web of filaments, walls, and voids we observe today. The statistical properties of these primordial fluctuations carry specific predictions that can be tested against observations. Inflation predicts that the fluctuation should be nearly scale invariant, meaning that variations on large scales have approximately the same amplitude as those on small scales. It predicts that the fluctuation should be Gaussian, following the bell curve distribution characteristic of random processes. And it predicts specific relationships between fluctuations in matter density and fluctuations in the geometry of spacetime itself. The cosmic microwave background provides the primary test of these predictions. This radiation, released approximately 380,000 years after the Big Bang when the universe cooled enough for atoms to form, carries an imprint of the density fluctuations present at that epoch. Hot spots in the cosmic microwave background correspond to regions of higher density, while cold spots correspond to underdense regions. By mapping these temperature variations across the sky with increasing precision, satellites have confirmed inflationary predictions with remarkable accuracy. The Planck satellite, launched in 2009, mapped the cosmic microwave background with unprecedented resolution and sensitivity. Its measurements confirmed that the fluctuation spectrum is nearly scale invariant, with a slight tilt towards stronger fluctuations at larger scales, precisely as many inflationary models predict. The fluctuations are Gaussian to high precision, with no significant detection of the non-Gaussian signatures that some alternative theories would produce. The relationship between density and geometric fluctuations matches inflationary expectations. By almost every measure, inflation's predictions have been spectacularly confirmed, yet questions remain, particularly concerning the larger scales. The cosmic microwave background exhibits several anomalies at large angular separations that have resisted explanation within standard inflationary models. The amplitude of fluctuations on the larger scales appears slightly lower than expected, a deficit that could indicate new physics or could simply reflect statistical fluctuation. Certain large-scale patterns show unexpected alignments that may or may not be significant. These anomalies are subtle and their interpretation contested, but they hint that our understanding of primordial fluctuations may be incomplete. The existence of structures like the Hercules corona borealis Great Wall adds another dimension to these questions. If inflation produced fluctuations with strictly scale-invariant amplitude, the largest structures we observe should be predictable from the smaller scale fluctuations measured in the cosmic microwave background. Structures significantly larger or more prominent than these predictions would suggest departures from simple scale invariance, perhaps indicating features in the inflationary potential or additional physics beyond the minimal model. Some inflationary scenarios naturally produce enhanced fluctuations at specific scales. If inflation occurred in multiple stages, or if the inflaton field encountered features in its potential energy landscape, the resulting fluctuation spectrum could deviate from perfect scale invariance in detectable ways. These deviations might enhance the probability of forming extremely large structures, providing a mechanism for producing walls spanning billions of light years. Testing such scenarios requires precise measurements of structure on the largest accessible scales, measurements that current surveys are only beginning to provide. The connection between inflation and the largest cosmic structures spans an almost inconceivable range of scales. Quantum fluctuations smaller than atoms were stretched to dimensions exceeding billions of light years, seeding the formation of structures that would take billions of years to grow. The Hercules corona borealis Great Wall, observed through gamma-ray bursts occurring in distant galaxies, ultimately traces its origin to processes that occurred in the first instant of cosmic existence. Understanding this connection requires bridging quantum mechanics and general relativity, particle physics and cosmology, the smallest known scales and the largest. It is a challenge that lies at the frontier of human knowledge. The observable universe extends approximately 46 billion light-years in every direction, a sphere centered on Earth containing everything we can ever hope to detect, with light or any other signal traveling at or below the speed of light. This boundary is not a physical wall but a horizon, the limit beyond which light has not had time to reach us since the Big Bang. The Hercules corona borealis Great Wall, spanning 10 billion light-years, occupies a substantial fraction of this observable volume. But the observable universe is almost certainly not the entire universe, and structures larger than anything we have detected may exist beyond our cosmic horizon, forever hidden from view. The distinction between the observable universe and the universe as a whole is fundamental yet often overlooked. When astronomers discuss cosmic structure, they implicitly mean structure within the observable volume, the only region accessible to observation. The universe beyond this horizon might continue indefinitely with similar properties, or it might differ dramatically in ways we cannot detect. Inflation suggests that the total universe vastly exceeds the observable portion, potentially by factors so large that the observable universe represents an infinitesimally small sample of the whole. The size of the observable universe is determined by two factors: the age of the cosmos and the expansion history of space. Light travels at a finite speed, approximately 300,000 kilometers per second, and the universe has existed for only 13.8 billion years. One might therefore expect the observable universe to extend 13.8 billion light-years in every direction, but this naive calculation neglects the expansion of space itself. During the time that light from distant sources has been travelling toward us, space has been stretching, carrying those sources farther away. A galaxy whose light has travelled for 13 billion years is no longer 13 billion light-years distant. Expansion has carried it much farther during the journey. The current proper distance to the most remote observable objects exceeds 46 billion light-years, more than 3 times the distance their light has actually travelled. This counterintuitive result reflects the dynamic nature of space in an expanding universe. The cosmic horizon marks the limit beyond which light emitted at the beginning of time has not yet reached us. Objects beyond this horizon are not merely too faint to detect. Their light literally has not had time to arrive, regardless of how powerful our telescopes might become. This horizon is not static, but grows with time as light from ever more distant regions finally reaches us. In the distant future, observers will have access to a larger observable volume than we do today, able to see structures currently beyond our horizon. However, cosmic expansion complicates this picture. The universe is not merely expanding but accelerating, driven by dark energy that causes distant regions to recede from us ever faster. At sufficient distances, this recession exceeds the speed of light, not because anything is moving through space faster than light, but because space itself is stretching faster than light can traverse it. Regions beyond a certain distance are receding so rapidly that light emitted from them today will never reach us, regardless of how long we wait. This creates a second horizon, the cosmic event horizon, beyond which events occurring now will remain forever unobservable. Unlike the particle horizon that grows with time, the event horizon is shrinking as cosmic acceleration intensifies. Regions currently within our event horizon will eventually pass beyond it, their light red shifted to infinity, and their signals lost to us permanently. In the far future, observers will inhabit an increasingly isolated observable universe, surrounded by an ever-growing volume of space from which no information can ever arrive. These horizons impose absolute limits on our knowledge of cosmic structure. The Hercules Corona Borealis Great Wall, at 10 billion light-years, lies well within the observable universe, accessible to current observations despite its extreme distance. But if similar or larger structures exist beyond 46 billion light-years, we will never know. The universe might contain walls spanning hundreds of billions of light-years, concentrations of matter dwarfing anything we have observed, and we would have no means of detecting them. This limitation has profound implications for cosmology. The cosmological principle assumes that the universe is homogeneous on large scales, but we can only test this assumption within the observable volume. If the observable universe happens to occupy an atypical region, our conclusions about cosmic properties could be systematically biased. The largest structures we observe might represent fluctuations that average out on scales larger than we can see, or they might hint at inhomogeneities that extend far beyond our horizon. Some theoretical models suggest that the universe beyond our horizon differs dramatically from what we observe. Eternal inflation, a variant of inflationary theory, proposes that inflation continues indefinitely in most of space, with the isolated regions like our observable universe forming as bubbles where inflation ends. These bubble universes might have different physical properties, different values of fundamental constants, even different numbers of spatial dimensions. If eternal inflation is correct, our observable universe is one island among countless others in an infinite inflationary sea, each island potentially harbouring different physics and different structures. The multiverse hypothesis, while speculative, addresses certain fine-tuning puzzles in physics. The constants of nature appear precisely calibrated to allow complex structures like atoms, stars, and life to exist. Slight variations would produce universes incapable of supporting complexity. If only one set of constants is possible, this fine-tuning demands explanation. But if countless universes exist with varying constants, our universe's properties reflect selection effects. We observe fine-tuned constants because only fine-tuned universes produce observers to notice them. This anthropic reasoning is controversial, criticized by some as unfalsifiable and by others as an abandonment of traditional scientific explanation, yet it emerges naturally from certain well-motivated physical theories, particularly string theory combined with eternal inflation. Whether the multiverse represents genuine reality or mathematical abstraction remains actively debated, with implications extending beyond cosmology to the foundations of science itself. Returning to observable structures, the limits imposed by cosmic horizons ensure that the Hercules Corona Borealis Great Wall, or something close to it, may represent the practical maximum for detectable structures. As structures approach the size of the observable universe, they become increasingly difficult to characterize because we lack the surrounding context needed to define their boundaries. A structure spanning half the observable universe would have no clearly defined exterior within our observable volume, making its extent fundamentally ambiguous. Furthermore, structures at extreme distances are observed as they existed billions of years ago, not as they exist today. The Hercules Corona Borealis Great Wall is seen at a look-back time of approximately 10 billion years, revealing its state when the universe was less than 4 billion years old. The structure has continued to evolve during the subsequent 10 billion years, but we cannot observe this evolution directly. By the time light from its current state reaches us, billions more years will have passed, and the universe will have changed further still. This temporal limitation intertwines with the spatial horizon to create a four-dimensional boundary around our knowledge. We observe a light cone, a slice through space-time that recedes in both space and time as we look to greater distances. The most distant objects are also the youngest in our observations, seen as they existed in the early universe. The present state of distant structures is hidden behind the finite speed of light, accessible only through inference and extrapolation. At what point does a collection of galaxies, clusters, and filaments cease to be a distinct structure and become simply the universe itself? This question, seemingly philosophical, carries practical implications for how astronomers identify and characterize the largest cosmic features. The Hercules Corona Borealis Great Wall spans 10 billion light-years, approximately 1/9 of the observable universe's diameter. If a structure were discovered spanning half or 3/4 of the observable volume, would it still constitute a structure in any meaningful sense, or would it simply represent an unusually dense region of the cosmos as a whole? The definition of structure requires contrast. A mountain is recognizable because it rises above the surrounding plain. An island exists because water separates it from other land. Similarly, cosmic structures are defined by their overdensity relative to surrounding regions. A galaxy cluster contains more matter per unit volume than the cosmic average. A great wall exhibits enhanced galaxy density compared to the voids on either side. Without this contrast, the concept of structure loses meaning. A perfectly uniform distribution would contain no structures at all, merely undifferentiated substance. As structures approach the size of the observable universe, the ability to establish contrast diminishes. The surrounding underdense regions that would define a structure's boundaries may lie partially or entirely beyond the cosmic horizon, inaccessible to observation. A hypothetical wall spanning 30 billion light-years would extend across most of the observable volume, leaving little room for the voids that would establish its identity as a distinct feature. At some scale, the distinction between structure and background becomes impossible to draw. This conceptual challenge reflects deeper questions about the nature of cosmic organization. The hierarchical model of structure describes a nested sequence of ever larger systems: stars within galaxies, galaxies within clusters, clusters within superclusters, superclusters within the cosmic web. Each level exhibits characteristic properties and formation mechanisms, though gravity underlies them all. But does this hierarchy continue indefinitely, or does it terminate at some maximum scale, where structures give way to homogeneity? The cosmological principle asserts that the hierarchy terminates, that above some scale the universe appears smooth and uniform. Galaxy surveys have sought to identify this homogeneity scale, the distance above which matter distribution becomes statistically indistinguishable from uniform. Early estimates place this scale around 250 million light-years, but discoveries of progressively larger structures have pushed the estimate ever higher. If structures spanning 10 billion light-years exist, the homogeneity scale must exceed this value, assuming it exists at all. Some researchers have questioned whether a homogeneity scale exists in any practical sense. The universe might be structured at all observable scales, with ever larger features emerging as surveys probe larger volumes. This fractal cosmology proposes that the universe exhibits similar patterns at all magnifications, with no preferred scale at which homogeneity emerges. While extreme versions of fractal cosmology have been ruled out by observations, milder versions remain viable, suggesting that complete homogeneity may require scales larger than the observable universe itself. The identification of structures also depends on the methods used to detect them. Different traces, such as galaxies, quasars, and gamma-ray bursts, sample different populations and different cosmic epochs. A structure visible in one tracer might be absent or differently configured in another. The Hercules Corona Borealis Great Wall was detected through gamma-ray burst distributions, but its appearance in optical galaxy surveys remains less certain. This tracer dependence complicates efforts to characterize structures definitively, as different methods may yield different boundaries and extents. Statistical methods for identifying structures also carry implicit assumptions that affect results. Algorithms that search for density enhancements must specify thresholds defining what constitutes significant overdensity. Lower thresholds produce larger structures by including marginally overdense regions. Higher thresholds produce smaller, more concentrated features. The choice of threshold is somewhat arbitrary, reflecting scientific judgment rather than physical necessity. Different researchers using different thresholds may reach different conclusions about whether a given feature constitutes a genuine structure. The boundaries of cosmic structures are inherently fuzzy. Unlike a planet with a well-defined surface, a galaxy wall fades gradually into its surroundings. The density of galaxies decreases smoothly from the wall's center to its edges, with no sharp transition marking inside from outside. Defining the wall's extent requires imposing an artificial boundary, typically where density drops below some specified fraction of the central value. This boundary is a human convention, not a physical feature of the structure itself. These considerations suggest that the largest cosmic structures may be partially artifacts of methodology, their sizes and shapes influenced by the tools used to detect and characterize them. This does not mean the structures are not real. Enhanced densities spanning billions of light years genuinely exist and require explanation. But the precise extent of these enhancements depends on definitions and methods that admit some flexibility. At the same time, certain features are robust across different methods and traces. The existence of the cosmic web, with its filaments, walls, and voids, is confirmed by multiple independent observations using different techniques. The approximate scales of the largest features are consistent across studies, even if precise boundaries vary. The challenge to the cosmological principle posed by giant structures is genuine, regardless of uncertainties in their exact dimensions. The question of when a structure becomes the universe itself may ultimately be unanswerable within our observable volume. If homogeneity emerges only at scales exceeding what we can see, we have no way to verify this empirically. The largest structures accessible to observation might represent the high end of a distribution that extends to even larger scales beyond our horizon, or they might mark the approach to genuine cosmic uniformity just beyond our view. Without access to larger volumes, we cannot distinguish these possibilities. This epistemological limit frames all conclusions about cosmic structure. The Hercules Corona Borealis Great Wall is the largest known structure, but known must be understood in context. It is the largest structure detectable within the observable universe using current methods. Larger structures might exist beyond our horizon, or might exist within our horizon but remain undetected due to observational limitations. The record holder of today might be surpassed by discoveries of tomorrow until the fundamental limits of observation are reached. What remains certain is that the universe exhibits structure across an extraordinary range of scales. From atomic nuclei to great walls spanning billions of light years, matter organizes itself into patterns that reflect the physical laws governing its behavior. The Hercules Corona Borealis Great Wall represents one extreme of this organization, a feature so vast that its existence challenges our assumptions and theories. Understanding why such structures exist, and whether they represent the ultimate limit of cosmic organization, remains one of the great open questions in cosmology. The standard model of cosmology known as lambda CDM, has proven remarkably successful at explaining the universe's large-scale properties. Lambda refers to the cosmological constant, a form of dark energy driving the accelerating expansion of space. CDM stands for cold dark matter, the invisible component providing the gravitational scaffolding for structure formation. Together, these ingredients, combined with ordinary matter and radiation, produce predictions that match observations across a wide range of scales and epochs. Yet the existence of structures like the Hercules Corona Borealis Great Wall strains this model's explanatory power, suggesting that our understanding of cosmic evolution may be incomplete. Lambda CDM emerged from decades of observational and theoretical progress. Einstein's general relativity provided the mathematical framework for describing gravity and space-time on cosmic scales. Hubble's discovery of cosmic expansion established that the universe was dynamic rather than static. The detection of the cosmic microwave background confirmed the hot, dense, early state predicted by Big Bang theory, and meticulous measurements of galaxy distributions, supernova distances, and microwave background fluctuations constrained the model's parameters with increasing precision. The model's 6 primary parameters describe the universe's composition and initial conditions. The density of ordinary matter, and dark energy determines how space expands and how structures grow. The amplitude and spectral index of primordial fluctuations specify the seeds from which all structure developed. And the optical depth to ionization characterizes how early galaxies ionize the intergalactic medium. With these 6 numbers, lambda CDM predicts everything from the temperature fluctuations in the cosmic microwave background to the distribution of galaxies in the present-day universe. The agreement between prediction and observation is impressive. The cosmic microwave background's statistical properties match lambda CDM expectations with precision approaching 1%. The abundance of galaxy clusters as a function of mass and redshift follows predicted trends. The large-scale distribution of galaxies exhibits the expected pattern of clustering, with correlations declining at larger separations precisely as the model predicts. Baryon acoustic oscillations, the imprint of sound waves in the early universe, appear at the predicted scale in both the microwave background and galaxy surveys. Yet this success has been achieved primarily at intermediate scales, from millions to hundreds of millions of light-years. At the largest accessible scales, tensions emerge. The cosmic microwave background shows less power at large angular separations than lambda CDM predicts, a deficit that remains unexplained. Certain large-scale patterns in the microwave background exhibit unexpected alignments that may indicate departures from statistical isotropy, and the existence of structures spanning billions of light-years challenges predictions about the maximum scale of cosmic organization. The Hercules Corona Borealis Great Wall, at 10 billion light-years, exceeds the theoretical limit for coherent structure formation by roughly an order of magnitude. Standard calculations based on lambda CDM suggest that structures should not exceed approximately 1 billion light-years, above which gravitational interactions have not had sufficient time to produce correlated concentrations of matter. The existence of larger structures implies either that these calculations are missing important physics, or that the observed structures are not coherent in the sense the calculations assume. Several modifications to lambda CDM have been proposed to accommodate anomalously large structures. One approach involves altering the primordial fluctuation spectrum, allowing enhanced power at very large scales. Standard inflation predicts a nearly scale-invariant spectrum, with fluctuation amplitude varying only slowly with scale. But this prediction rests on assumptions about the inflationary potential that might not hold exactly. If inflation produced stronger fluctuations at large scales, the resulting overdensities could seed larger structures than standard calculations predict. Another approach considers modifications to gravity itself. General relativity has been tested extensively at solar system scales and in binary pulsar systems, but its behavior at cosmological distances is less directly constrained. Modified gravity theories, originally developed to explain cosmic acceleration without dark energy, might also affect structure formation in ways that permit larger coherent features. These theories must satisfy stringent observational constraints, ruling out many possibilities, but viable alternatives remain under investigation. The nature of dark matter also affects structure formation predictions. Lambda CDM assumes dark matter is cold, meaning dark matter particles move slowly compared to light, and can clump efficiently on small scales. But dark matter might have properties that differ from this assumption. Warm dark matter, consisting of faster moving particles, would suppress structure formation on small scales, while potentially allowing larger structures to form. Self-interacting dark matter, where particles collide with each other rather than passing freely, would alter the internal structure of halos and might affect large-scale distributions. Each alternative makes distinct predictions that can be tested against observations. The Hubble tension represents another challenge to lambda CDM with potential implications for structure formation. Measurements of the cosmic expansion rate using local distance indicators, such as Cepheid variables and Type Ia supernovae, yield values approximately 10% higher than those derived from the cosmic microwave background assuming lambda CDM. This discrepancy, now exceeding 5 standard deviations in statistical significance, suggests either unrecognized systematic errors in the measurements or new physics beyond the standard model. Proposed resolutions to the Hubble tension often invoke early universe modifications that would also affect structure formation. Additional relativistic species in the early universe, decaying dark matter, or early dark energy could alter the expansion history in ways that reconcile local and cosmological measurements. Some of these modifications would change the growth rate of structures, potentially permitting larger features than standard lambda CDM allows. The connection between the Hubble tension and anomalously large structures remains speculative, but both phenomena point toward possible gaps in current understanding. The sigma-8 tension provides yet another hint of discrepancy. This parameter characterizes the amplitude of matter fluctuations on scales of approximately 8 megaparsecs, roughly 25 million light-years. Measurements from galaxy clusters and gravitational lensing tend to yield lower values than predictions based on the cosmic microwave background and lambda CDM. If the universe is less clumpy on intermediate scales than expected, the implications for structure at larger scales remain unclear, but the tension suggests that matter distribution may not follow lambda CDM predictions precisely. These various tensions and anomalies do not yet constitute a crisis for lambda CDM. The model remains the best available description of the universe across most observable scales and epochs. But the accumulation of discrepancies, including the existence of structures far larger than predicted, motivates continued scrutiny and the exploration of alternatives. The next generation of observations may either resolve these tensions within the standard framework or reveal departures requiring fundamentally new physics. The coming decades promise unprecedented advances in our ability to map the universe's large-scale structure. New telescopes, survey instruments, and observational techniques will extend cosmic cartography to depths and scales previously inaccessible. These future surveys may reveal structures larger than any currently known, or they may establish that the Hercules Corona Borealis Great Wall represents the practical limit of cosmic organization. Either outcome will transform our understanding of the universe's architecture and the physical processes that shaped it. The Dark Energy Spectroscopic Instrument, which began full operations in 2021, represents the current state-of-the-art in large-scale structure surveys. Located at Kitt Peak National Observatory in Arizona, this instrument uses 5,000 robotic fiber positioners to capture spectra from thousands of galaxies and quasars simultaneously. Over its 5-year primary mission, it will measure redshifts for approximately 40 million objects, creating a 3-dimensional map of unprecedented scope. The survey targets multiple classes of objects at different distances, providing complementary views of cosmic structure across cosmic time. Bright galaxies at relatively modest distances trace structure in the nearby universe, where the cosmic web can be mapped in fine detail. Luminous red galaxies extend the mapping to intermediate distances, where the universe was approximately half its current age. Emission-line galaxies probe still greater depths, reaching epochs when the universe was only a few billion years old. And quasars, the most luminous objects in the cosmos, mark structure at the greatest accessible distances, when the universe was young and structure formation was still in its early stages. The scientific goals of the Dark Energy Spectroscopic Instrument extend beyond mapping alone. By measuring baryon acoustic oscillations, the imprint of sound waves from the early universe frozen into the galaxy distribution, the survey will constrain cosmic expansion history with unprecedented precision. These measurements will test whether dark energy is truly constant, as assumed in lambda CDM, or varies with time in ways that would require new physics. The survey will also measure the growth rate of structure through redshift space distortions, the apparent clustering pattern caused by galaxy motions toward dense regions. Comparing these measurements against lambda CDM predictions will either confirm the standard model or reveal deviations requiring explanation. The Euclid mission, launched by the European Space Agency in 2023, complements ground-based surveys with observations from space. Freed from atmospheric distortion and the bright sky background that limits ground-based telescopes, Euclid will image billions of galaxies across more than one-third of the sky. Its primary technique is weak gravitational lensing, the subtle distortion of galaxy shapes caused by intervening mass along the line of sight. By measuring these distortions statistically across millions of galaxies, Euclid will map the distribution of dark matter directly, revealing the gravitational scaffolding upon which visible structure is built. Weak lensing provides a view of cosmic structure fundamentally different from galaxy surveys. Galaxies trace mass only approximately, as the relationship between galaxy density and underlying dark matter density depends on complex astrophysical processes that vary with galaxy type, environment, and cosmic epoch. Gravitational lensing, by contrast, responds directly to mass regardless of its form, providing an unbiased tracer of total matter distribution. Comparing lensing maps with galaxy distributions reveals the bias between visible and total matter, illuminating the processes by which galaxies form within dark matter halos. The Vera C. Rubin Observatory, under construction in Chile, will conduct the Legacy Survey of Space and Time beginning in 2025. This ambitious project will repeatedly image the entire southern sky every few nights for 10 years, creating a movie of the changing universe that will enable discoveries across nearly every field of astronomy. For large-scale structure studies, the survey will provide photometric redshifts for billions of galaxies, estimating distances from multicolor imaging rather than spectroscopy. While less precise than spectroscopic redshifts, photometric techniques can be applied to far larger samples, mapping structure across enormous volumes. The combination of these surveys, along with others in development, will create a comprehensive picture of cosmic structure from the present day back to when the universe was only 1 billion years old. Different surveys will map different volumes, probe different traces, and employ different techniques, but their combined results will be far more powerful than any individual project. Cross-correlations between datasets will reveal systematic effects and break parameter degeneracies that limit individual analyses. The era of precision cosmology will extend from the cosmic microwave background, where it began, to the large-scale structure of the present-day universe. Radio astronomy offers another window into cosmic structure that future facilities will exploit. The Square Kilometre Array, an international project spanning sites in South Africa and Australia, will be the largest radio telescope ever built when completed. Its enormous collecting area will enable surveys of neutral hydrogen, the most abundant element in the universe, across cosmic history. Before the first stars formed, neutral hydrogen filled the universe, absorbing and emitting radiation at a characteristic wavelength of 21 centimeters. By mapping this emission at different redshifts, the Square Kilometre Array will trace structure formation through the cosmic dark ages and into the epoch of Orionization, when the first luminous objects transformed the intergalactic medium. Intensity mapping represents a particularly promising technique for probing the largest scales. Rather than detecting individual galaxies, intensity mapping measures the aggregate emission from all sources within large volumes, trading angular resolution for sensitivity to diffuse structure. This approach can efficiently map enormous volumes, potentially revealing features at scales inaccessible to traditional galaxy surveys. Experiments targeting various emission lines, including hydrogen, carbon monoxide, and ionized carbon, are under development or already collecting data. Gravitational wave astronomy, inaugurated by the first detection of merging black holes in 2015, may eventually contribute to large-scale structure studies. Merging compact objects serve as standard sirens, sources whose gravitational wave signals encode their distances directly through general relativity. Combined with electromagnetic observations identifying host galaxies, these measurements provide distance indicators independent of the traditional cosmic distance ladder. Future gravitational wave observatories, including the space-based laser interferometer Space Antenna planned for the 2037 will detect mergers across cosmological distances, potentially mapping structure through an entirely new channel. The question of whether structures larger than the Hercules Corona Borealis Great Wall exist may be answered by these future surveys, or it may remain forever open. If larger structures exist within the observable universe, expanded surveys covering greater volumes with more tracers should reveal them. But if the Hercules Corona Borealis Great Wall represents the largest coherent feature accessible to observation, future surveys will instead characterize it more precisely, determining its exact extent, internal structure, and relationship to surrounding features. Either outcome will advance our understanding of the universe's larger scales, confronting structures that span significant fractions of the observable universe forces a reckoning with scale that transcends scientific analysis. The Hercules Corona Borealis Great Wall, at 10 billion light-years, challenges not only cosmological models, but human comprehension itself. Numbers at this magnitude become abstractions, quantities that can be written and manipulated mathematically, but cannot be truly grasped by minds evolved to navigate environments measured in meters and kilometers. Yet engaging with these scales, however imperfectly, offers a perspective on existence that few other endeavors can provide. The history of astronomy is largely a history of expanding scales. Ancient observers saw the sky as a celestial dome, perhaps resting atop a flat Earth or enclosing a spherical one. The sun, moon, and planets moved against this backdrop, their distances unknown and perhaps unknowable. The stars were points of light fixed to the dome's inner surface, ornaments in a cosmos centered on human habitation. This geocentric universe, however sophisticated its mathematical description became in Ptolemaic astronomy, remained fundamentally human-scaled, a stage for terrestrial drama. The Copernican revolution displaced Earth from the cosmic center, but the full implications took centuries to unfold. Even after accepting that Earth orbited the Sun, astronomers had little sense of stellar distances. The first successful parallax measurements in the 1830s revealed that even the nearest stars lay trillions of kilometers away, distances so vast that new units were required to express them sensibly. The light year entered astronomical vocabulary as a measure appropriate to the newly discovered gulfs between stars. The recognition that the Milky Way was an island of stars in a vastly larger cosmos came only in the 20th century. Hubble's measurement of the Andromeda Galaxy's distance in 1924 revealed that the universe extended far beyond our stellar neighbourhood, containing countless other galaxies separated by millions of light-years. The observable universe expanded by orders of magnitude in a single discovery, yet even this dramatic expansion represented only a step toward current understanding. Galaxy clusters, superclusters, and the cosmic web each added layers to the hierarchy of structure, pushing the scale of organization ever higher. The original Great Wall, at 500 million light-years, seemed almost incomprehensibly large when discovered in 1989. Within 3 decades, structures 20 times larger had been identified, stretching across spans that light itself requires billions of years to cross. Each discovery has reinforced a humbling truth. The universe is larger, more structured, and more complex than any previous generation imagined. This progression raises questions about humanity's place in the cosmos that science alone cannot fully answer. The Copernican principle, which denies any privileged position for Earth or its inhabitants, has been progressively confirmed by every expansion of cosmic scale. We occupy no special location, orbit no special star, reside in no special galaxy. The Milky Way is one among hundreds of billions of galaxies in the observable universe, itself perhaps an infinitesimal fraction of a vastly larger whole. Against structures spanning 10 billion light-years, human civilization is less than a speck, a momentary arrangement of matter in an inconceivably vast arena. Yet this apparent insignificance admits alternative interpretations. The same cosmic processes that built the Hercules Corona Borealis Great Wall also built the atoms in human bodies, forged in stellar interiors and scattered by supernova explosions. The elements that compose living tissue, the carbon, oxygen, nitrogen, and iron essential to biology, were synthesized in stars that lived and died billions of years ago, their processed material eventually incorporated into planets and the life they support. In this sense, life represents the universe examining itself, matter organized to contemplate its own origins and structure. The ability to detect and characterize structures spanning billions of light years is itself remarkable. Humans have existed for perhaps 300,000 years, a duration insignificant compared to cosmic timescales. Modern science emerged only a few centuries ago, and the technologies enabling large-scale structure surveys are products of the past few decades. In an evolutionary eye blink, a species confined to one planet developed the capacity to map significant fractions of the observable universe, identifying patterns that formed billions of years before Earth existed. This achievement reflects something profound about the relationship between mind and cosmos, a connection that science illuminates but does not fully explain. Different philosophical and religious traditions interpret cosmic scale in different ways. Some find in the universe's vastness evidence for transcendent purpose, a creation whose grandeur reflects its creator's nature. Others see cosmic immensity as confirming the absence of such purpose, a universe indifferent to human concerns precisely because it operates through impersonal physical law. Still, others locate meaning not in the cosmos itself, but in the human response to it, the capacity for wonder, inquiry, and creativity that astronomical discovery exemplifies. These interpretations exceed what science can adjudicate, belonging instead to philosophy, theology, and personal reflection. What science can offer is precision about what we know and do not know. The Hercules corona borealis Great Wall exists, a concentration of matter spanning 10 billion light-years detected through the distribution of gamma-ray bursts. Its formation challenges current theoretical models, suggesting either incomplete understanding of structure formation or previously unrecognized features in the primordial fluctuation spectrum. Its existence, along with other giant structures, strains the cosmological principle that has guided cosmology for nearly a century. These are factual statements, subject to revision, as observations improve but grounded in evidence rather than speculation. The emotional response to such facts varies among individuals. Some experience awe at the universe's scale, a sense of wonder that motivates scientific inquiry and enriches human experience. Others feel anxiety or insignificance when confronting cosmic vastness, finding the disproportion between human and cosmic scales troubling rather than inspiring. Neither response is more valid than the other. Both reflect legitimate human reactions to discoveries that exceed ordinary experience. Science provides the facts. What meaning they carry remains a matter for each person to determine. The study of cosmic structure continues regardless of philosophical interpretation. Astronomers map the universe not primarily to derive existential lessons, but to understand physical reality, to test theories, and discover new phenomena. The Hercules corona borealis Great Wall poses scientific puzzles that demand scientific solutions, questions about formation mechanisms, observational completeness, and theoretical adequacy. Answering these questions requires better observations, more sophisticated simulations, and perhaps new theoretical frameworks. The work proceeds through the methods of science, accumulating knowledge incrementally through evidence and argument. The Hercules corona borealis Great Wall raises more questions than it answers. Its existence, confirmed through gamma-ray burst distributions and supported by subsequent analyses, represents a challenge to cosmological understanding that remains unresolved. The largest known structure in the observable universe stands as a testament both to human ingenuity in detecting features across billions of light-years and to the limits of current theory in explaining how such features could form. As this exploration of cosmic scale concludes, the questions that remain open deserve explicit acknowledgement, for they point toward the frontiers of knowledge where future discoveries await. The most fundamental question concerns the structure's reality and extent. While multiple analyses support the existence of an overdensity in the Hercules corona borealis region, the precise boundaries and internal organization remain uncertain. Gamma-ray bursts, though powerful traces of distant structure, provide a sparse sampling compared to galaxy surveys. The statistical significance of the detected concentration, though high, admits some possibility of chance alignment or systematic effects. Future observations using different traces, particularly deep galaxy surveys probing the relevant redshift range, will either confirm the structure's extent or reveal it to be smaller or more fragmented than current estimates suggest. The formation mechanism presents another profound puzzle. Standard cosmological models based on lambda CDM cannot readily produce coherent structures spanning 10 billion light-years. The time since the Big Bang is insufficient for gravity to correlate matter across such distances, given the finite speed at which gravitational influence propagates. Either the structure is not coherent in the sense these calculations assume, representing instead a chance superposition of smaller independent features, or something is missing from the standard formation picture. Identifying what that something might be remains an open theoretical challenge. Modifications to the primordial fluctuation spectrum offer one potential resolution. If inflation produced enhanced fluctuations at very large scales, the seeds for giant structures could have been planted in the universe's first moments. Such enhancements might arise from features in the inflationary potential, multiple stages of inflation, or other departures from the simplest inflationary scenarios. Testing these possibilities requires precise measurements of the fluctuation spectrum at scales larger than those probed by current cosmic microwave background observations, a challenging but potentially achievable goal for future experiments. The relationship between the Hercules Corona Borealis Great Wall and other giant structures also demands investigation. The Sloan Great Wall, the Huge Large Quasar Group, and the Giant Arc each represent independent discoveries of anomalously large features. Whether these structures share common origins, perhaps reflecting the same enhanced primordial fluctuations or similar formation pathways, remains unclear. Systematic studies comparing the properties of giant structures across different cosmic epochs could reveal patterns that illuminate their formation, or could demonstrate that each represents a distinct phenomenon requiring separate explanation. The challenge these structures pose to the cosmological principle remains unresolved. The assumption that the universe is homogeneous on large scales has guided cosmology for decades, providing the foundation for standard models of cosmic expansion and structure formation. Structures spanning 10 billion light-years suggest that homogeneity, if it exists at all, emerges only at scales approaching the observable universe itself. This possibility complicates cosmological inference, potentially introducing systematic biases into measurements that assume uniform matter distribution. Understanding whether the cosmological principle holds, and at what scale, is essential for interpreting virtually all cosmological observations. The question of whether larger structures exist beyond current detection limits also remains open. The Hercules Corona Borealis Great Wall was discovered through a method, gamma-ray burst mapping, that had not previously been applied to large-scale structure studies. Other methods, exploiting different tracers or analytical techniques, might reveal features that current approaches miss. The observable universe contains volumes not yet surveyed with sufficient depth or coverage to detect giant structures, and even well-surveyed regions might harbour features that current methods fail to identify. The record for largest known structure has been broken repeatedly over the past 3 decades. Whether it will be broken again depends on observations not yet made. Beyond the observable universe, the question of cosmic structure becomes entirely speculative. If the universe extends far beyond our horizon, as inflation suggests, structures of arbitrary size might exist in regions forever inaccessible to observation. Walls spanning hundreds of billions of light-years, or even larger, could populate a cosmos whose full extent dwarfs the observable volume. We will never know what lies beyond the horizon, but the structures within our view hint at organisational principles that might extend to scales we cannot imagine. The implications for fundamental physics also remain to be explored. The existence of giant structures might provide evidence for new particles, new forces, or new cosmological mechanisms not included in current models. Dark matter's properties, dark energy's nature, and gravity's behaviour at cosmological scales all affect structure formation in ways that observations might constrain. The tension between observed structures and theoretical predictions could point toward discoveries that transform our understanding of physical law, much as previous anomalies have led to revolutionary advances. The human dimension of these questions should not be overlooked. The scientist who discovered and characterized the Hercules Corona Borealis Great Wall, who built the instruments that detected gamma-ray bursts across cosmic distances, and who developed the theories that frame our understanding all represent human effort applied to understanding the universe. This effort continues in observatories around the world and in space, in universities and research institutes, wherever curiosity about the cosmos motivates systematic inquiry. The questions raised by giant structures will be answered, if they are answered at all, through the persistent application of scientific method by researchers yet to make their contributions. The Hercules Corona Borealis Great Wall, the largest object humanity has ever found in the universe, stands as both an achievement and a challenge. Its discovery demonstrates that cosmic structure extends to scales barely conceivable a generation ago. Its existence challenges the theoretical frameworks that have guided cosmology for decades, and the questions it raises point toward discoveries yet to come, insights that will further expand human understanding of the universe we inhabit. 10 billion light-years across, this vast concentration of matter reminds us that the cosmos remains full of surprises, that the project of understanding it is far from complete, and that the larger scales accessible to observation still hold secrets waiting to be revealed.